சார்.
Sir, good morning, sir.
Muthu, good morning. Muthu, good morning.
Sir, good morning, sir. I'm Ganapati,
good morning,
sir.
Yeah, Ganapati, sir. Good morning. Good morning. So, இப்போ யூடியூப்பும் லைவ் வந்துட்டு இருக்குங்களா?
இந்த முத்து ட்ரை பண்ணிட்டு இருக்கா சார். கனெக்ட் பண்ணிருக்கா சார்.
ஓகே. ஸ்டூடண்ட்ஸ் இன்னும் வர ஆரம்பிக்கலையா?
இந்த ஒரு டீம் அட்மின் பண்ணிட்டு இருக்காங்க சார்.
சரிங்க சார். ஓகே.
சார் யூடியூப் லைவ் வந்துட்டு இருக்கு. யூடியூப் லைவ் வந்துட்டு இருக்கு சார்.
ஓகே. நான் பாக்குறேன், செக் பண்றேன். உன்னோடதான் வாய்ஸ் வருது. முத்து, உன்னோடதான் வாய்ஸ் வருது. முத்து, உன்னோட கம்ப்யூட்டர் ஆன் பண்றப்ப நாய்ஸ் வருது முத்து, ப்ளீஸ் செக் இட். முத்து யூடியூப் லைவ்ல போயிட்டு இருக்கா முத்து?
சார் சார் மெயில் சென்ட் பண்ணிருக்கேன் உங்களுக்கு. யூடியூப் லிங்க் சென்ட் பண்ணிட்டேன் ஆல்ரெடி. உங்க மெயில் ஐடிக்கு சென்ட் பண்ணிருக்கேன்.
அந்த லிங்க் வந்து chat box போட்டு விட்டுருக்கேன்.
சரிங்க சார். chat boxல போட சொல்லிடுறேன் சார்.
ஆமா chat box போட்டீங்கன்னா எல்லாம்
ஓகே சார். ஓகே சார்.
So, Professor Muthuchami will join now. I spoke with you.
Sir, welcome, sir.
Yeah, he'll be joining soon. He joined already? Yeah. I called him.
Okay.
So, Muthu, YouTube is working perfectly.
Yes, sir. Yes, sir.
Yeah, I checked. Yeah.
Okay, sir.
So, இங்க எவ்வளவு ஸ்டூடண்ட் அட்மிட் பண்றீங்க?
எங்க ஸ்டூடண்டா சார்?
இதுல கூகுள் மீட்ல.
கூகுள் மீட்ல 90 சார்.
90. Okay.
Yes.
இன்னும் ஸ்டூடண்ட் ஜாயின் பண்ணிட்டு இருக்காங்களா? இன்னும் வரலையா?
Yes, sir. இப்பதான் just now they have finished exam.
Okay.
1:30க்கு எக்ஸாம் முடிஞ்சது அவங்களுக்கு.
Okay.
வந்துரும்.
Muthu?
Yes.
No, sir is joined already. Sir, welcome, sir.
Sir, welcome, sir.
Yes.
Sir, very warm welcome to you, sir. Sir, I tried several times. I could not connect with you, sir. Sorry, sir.
Okay, thank you.
So, Muthu will wait for a few more minutes or?
Yes, sir. Okay, sir. Just
No,
2 minutes we wait,
it's up
sir.
to you.
Okay,
Yeah. So, since in our college, principal and others are like,
Yeah. Yes, sir.
getting
Yes, sir.
ready. Let us know here online.
Okay, sir. LI Raja.
Yes, sir. Yes, sir.
Okay,
Yes, sir.
okay. You can start now.
Yeah, sir.
Okay.
Can I start, sir?
Yes,
sir.
okay.
Yes,
Yeah,
sir.
yeah.
So I feel extremely grateful to be with us the August gathering on this wonderful winter occasion on this e-lecture workshop program on advances in chemical science organized by Chemical Research Society of India CRSI Trichy-Madurai local chapter in amalgamation with PG and Research Department of Chemistry Vivekananda College Tiruvadagam West. A man is made by his belief, as he believes so he is. So with this Gita Upadesh, let me permit it to ignite this one-day e-lecture program with our usual prayer, Om Sahana Vavatu by all.
Om Sahana Bhavatu Sahanau Bhunaktu Sahaviryam Karavavahai Tejasvinavadhitamostu Ma Vidvishavahai Om Shanti Shanti Shanti.
Now your audio is
Listen.
muted.
Raja, unmute your.
Unmute your audio. Yes.
Sorry, sir. So a good leader is like an indicator who indicates the visual color changes at any medium after the equivalent point is reached. So I feel personally proud to call upon the most youngest active head of our department, Mr. B. Sevaramuthu sir, to welcome all by his wonderful words. Welcome you, sir.
Very good afternoon and all gathered here. Distinguished CRSI members, Revered Secretary Swamiji and Kulabadi Swamiji, dynamic principal of our college, respected conveners, esteemed resource persons, beloved staff members, and all participants from all over India. So BG and Research Department of Chemistry, Vivekananda College welcomes you to this National Chemistry Week 2020, which is the annual celebration of chemical science to create science awareness among the student community. Through e-lecture workshop on advances in chemical sciences during this COVID-19 period, organized by Department of Chemistry, Vivekananda College, Madurai, in collaboration with Chemical Research Society of India, Trichy-Madurai local chapter. I am very happy to welcome you all. On behalf of the organizing committee, I extend a warm welcome to Swami Vivekananda, Secretary, Swami Adhyatmananda Kulabadi, and Dr. T. Venkatesan, Principal of our college, and I thank our management for their support to organize event like this. And also I thank our management being a part and parcel of our department. I am very happy to welcome conveners Dr. R. Mail Murugan, School of Chemistry, Madurai Kamaraj University, and Professor R. Ramesh, Department of Chemistry, Bharathidasan University, Tiruchirappalli. I thank them who have made a lot of effort to bring all the big shots on a single platform and also selecting our college as host institute to organize this event. And also I am very happy to welcome the esteemed resource persons, Professor Muthuchami, Chair and Head, School of Chemistry, Bharathidasan University, and Professor Tilagar, Inorganic and Physical Chemistry Department, IISc Bangalore. And it is my great pleasure to welcome our proud alumnus, Professor Shankar, Department of Chemistry, IISER Pobal. It is my pleasure to welcome all other CRSI members who are participating in this event. Finally, I am very happy to welcome faculty members, researchers, and students from our premises and various delegates from all over India. Though we are in COVID-19 pandemic situation, I hope this event will fulfill its target via latest technologies, and I hope after this event, beneficiaries will contribute their best science to the society to sustain green environment. So on the outset, behalf of the Department of Chemistry, Vivekananda College, I submit my sincere thanks to members of CRSI, conveners, resource persons, all the well-wishers for your kind support to conduct this e-lecture workshop successful one. So once again, I welcome you all and thank you very much. I wish you all the best for this program. Thank you, sir.
Thank you, sir, for your nice welcome address. It's really feeling me good to welcome my teacher as well as the convener of this e-lecture workshop from my parent institution, Madurai Kamaraj University. Of course, Dr. R. Mail Murugan, sir, Assistant Professor, Department of Physical Chemistry, School of Chemistry, Madurai Kamaraj University, Madurai. And also, I request him to brief about this CRSI workshop. Welcome you, sir.
Thank you, Rajas, for your kind words. Firstly, I would like to thank Vivekananda College Management, the Principal, Secretary, and the Head of the Department for willing to organize such a nice event at your college. Of course, your alumni is the spread out all over India, not only in India, abroad also. They're all happy to visit your college and give a talk. Like Dr. Sangar is there, he's always wanted to give a talk in Madurai region since he is from Madurai. Firstly, I would like to brief about the CRSI, the Chemical Research Society of India. It is established in 1999 in connection to the 50th Independence Day celebration of our nation. So right now we do have 2,800 like members. This institution is founded by Professor Sina Rao and his colleague. Right now, this CRSI is doing excellent activities like conducting annual and mid-year meeting. Not only this one, so we used to have local chapter meetings. We do have several local chapters. This local chapter used to visit different colleges to cultivate the chemical science research attitude among the students. So the main idea of the CRSI is to bring more students for the chemical science research. Also, for the college teachers, we do have a wonderful program. We used to award the best chemistry teacher award in every year. All the annual meetings. So we used to award several best chemistry teacher award. To apply for this award, all the college teachers should become a life member of CRSI. You may ask the question, what are the benefits you'll get out of this life membership? So you will go for an annual meeting with a discounted registration fee. Also, you can bring your students for a free of cost to attend this meeting so that they can meet several the young scientists, also the senior scientists, so that they will have more motivation to do chemical science research as a career. That's how the CRSI is performing very well. So in this occasion, I would like to thank all the speakers, Professor Muthuswamy and Professor Tilagar, for accepting our invitation to deliver the lectures. Right now, everyone is busy. So also I thank the colleagues, all the chemistry teacher in the Trichy-Madurai region for supporting us all the time. So the other convener, Professor Ramesh, is unable to join due to his personal work. He will join for other meeting. So about the National Chemistry Week. So right now, this is the 6th meeting we are conducting. Sorry, 5th meeting. 4 meetings already were on, 3 in Trichy region, another one in Vivekananda yesterday. This is the 5th meeting, 6th meeting will be tomorrow. So this is how the Trichy local chapter have organized several lecture series so that we can reach the students of every college. So with these few words, I just conclude my talk. Again, I thank all the speakers for accepting our invitation to deliver a lecture. Also, I thank the college management of Vivekananda College for hosting this this event at your college. Thank you so much.
Thank you, sir, for your crystal clear information on CRSI as well as lecture workshops also. Versatility is the outcome of your own passion. It's my great honor, which I feel, to call upon the man of versatility and, of course, the active, dynamic lead of our prestigious Gurukula Life Training Institute, Dr. T. Venkatesan, sir, Principal, to deliver his valuable presidential address. Welcome you, sir.
So first of all, I submit my pranams at the feet of our founder Swamiji, Swami Vivekananda, the most respected Secretary Swamiji of Vivekananda College, Swami Vivekananda, the most respected Kulabadi Swamiji, Swami Adhyatmananda, our beloved Vice Principal, Professor Parthasarathi, our beloved Dean and Controller, Dr. K. Karthikeyan, our beloved IQAC Coordinator, Dr. Shadish Babu, Head of the Department of Chemistry, Mr. Servaramuthu, conveners for this webinar, Dr. R. Mailmurugan and Dr. R. Ramesh, faculty members of this department, participants from various colleges, universities. So good afternoon to everyone. So first of all, I congratulate the team members of the Department of Chemistry organizing this webinar on e-lecture workshop on advances in chemical science. So my hearty congratulations to Chemical Research Society of India and the PG and Research Department of Chemistry of Vivekananda College. So our college gives prime importance to life training. So you all know. So this institution is a man-making institution, a Gurukula Institute for life training. So our institution is mainly focusing on various values, the value of physical culture, the value of spiritual culture, the value of silence, the value of conquering tongue, the value of community living, and the value of quest of excellence. So our college was established by our founder Swamiji, Swami Vivekananda, in the year 1971. So this college is an autonomous institution since 1987. So this institution was re-accredited with the A grade by NAC for 3 times. So this institution was also granted with the College with Potential for Excellence in the year 2016. So the Department of Chemistry was established in the year 1981-82 by introducing BSc Chemistry as a degree course. The MSc Chemistry, the postgraduate course in the year 2003-2004. So this department, the Department of Chemistry, was recognized as a research department by Vivekananda University from 2005 onwards. So this department is always motivating this scientific aptitude and a skill development in the minds of students to pursue higher studies with excellence in research in the field of green chemistry, then coordination chemistry, then spectromolecular chemistry, inorganic chemistry, and photochemistry. So there are more than 3,000 library books in the Department of Chemistry. So this department is headed by Sri P. Servaramuthu, Dr. M. Kanabadi, Dr. G. Rajkumar, Dr. M. Raghu, Dr. Tirupati, Dr. Balakrishnan, Sri Dharmanandam, and Dr. L.A. Raja are the faculty members of this department, the Department of Chemistry. Today, this department is jointly organizing this webinar along with the Chemistry Research Society of India. The topic is e-lecture workshops on advances in chemical sciences. So I congratulate the conveners of this webinar, Dr. Mail Murugan from School of Chemistry from Madurai Kamaraj University, and Dr. R. Ramesh, School of Chemistry from Bharathidasan University. The resource persons for this webinar, Professor S. Muthuswamy from Bharathidasan University, Professor P. Tilagar from Indian Institute of Science, Bangalore, Professor J. Shankar, our alumnus from IISR from Bhopal. So my hearty congratulations to all the resource persons of this webinar. Attending this webinar will enrich your knowledge in the field of advances in chemical sciences. So before I end, I would like to express my sincere thanks to all the resource persons and the faculty members of the Department of Chemistry. So I would like to express my wishes to all the participants. I once again wish this webinar a grand success. Thank you, Ananda.
Thank you, sir, for your fruitful and informative presidential address. Without further delay, let me move into our technical A-session 1 by Professor S. Muthuswamy, sir, Bharathidasan University, Trichy. For this, may I invite our beloved colleague, Dr. A. Kannan, sir, Assistant Professor of Chemistry, Department of Chemistry, Vivekananda College, to chair this session. Welcome you, sir.
Thank you, sir. Respected professors and beloved participants, very good afternoon all. I am privileged and happy to introduce Dr. S. Muthuswamy, sir, Professor in the Department of Chemistry and the Director, Research, Bharathidasan University, Trichy. He is well-known organic chemist in India. His biodata runs to many pages. So, here I briefly tell the achievements of our chief guest. Muthuswamy, sir, graduated with the MSc degree in PhD College of Arts and Science from Bharathidasan University and obtained doctoral degree in synthetic organic chemistry from University of Madras in 1992 after qualifying CRSI UGC National Eligibility Test. He subsequently held postdoctoral position at the Technical University, Brunswick and Ruhr University, Bochum, Germany, under Alexander von Humboldt Fellowship, and the University of Hyderabad, prior to joining as a scientist in Central Salt Marine Chemical and Research Institute, Bhavnagar, in 1997. Then he moved to Bharathidasan University as a professor in 2006. His research interest in the area of synthetic organic chemistry include chemistry of diazocarbonyl compounds, rhodium carbenoids, stereoselective synthesis, multi-component reaction, metathesis reaction, green chemistry, and synthesis of heterocyclic and macrocyclic system. He is a recipient of Tamil Nadu Scientist Award in 2018, Fellow of the Academy of Sciences, Chennai, Professor Vadia Award from University of Pune in 2013, 76th Indian Science Congress, Madurai Kamaraj University Eminent Scientist Award in 2009, CRSI Bronze Medal Award in 2006, Professor D.K. Banerjee Memorial Award from Indian Institute of Science in the year 2003, and the CSIR Young Scientist Award in Chemical Science in the year 1998. He has visited Germany and the United Kingdom. He is having around 100 publications, including research articles, patents, reviews, book chapters, monographs, and more than 75 invited lectures. Thank you. Now I invite and hand over the session to Professor Muthuswamy, sir. Please, sir.
Yeah, thank you very much for your kind introduction. So I must thank the local conveners, Dr. Ramesh and Mail Murugan, for providing this opportunity in CRSI local chapter meetings. And also I thank the principal of Vivekananda College and the head of the department of Vivekananda College, chemistry department, for hosting this event fruitfully. Let me share the file. So hope the slide is visible.
Yes, sir. Yes, sir.
Yeah. Okay. Okay. So thanks a lot. So let me start the topic on the principles and applications of NMR spectroscopy. I would like to provide in this session. Thinking that I'm not taking the research topic to the students, so at least this is related to the UG and PG and research students. So definitely everyone will be familiar with this topic a little bit already. And the UG students and PG students may be useful to them. At least they can listen more on this topic. So let me try to complete 40-45 minutes of this topic. It is a little tough to complete the complete principles and applications, and I have just taken the highlights of the NMR spectroscopy. So in this topic, I just took NMR concepts and then experiment, chemical shift, and coupling constant. So that means I'm just going to touch upon in this presentation only these 4 topics: concepts and experiments, chemical shift, and coupling constant. With the help of few slides, I will try to explain to the students' benefit. So the introduction is very short. So already the NMR spectroscopy technique is very important, and you can see that based on the Nobel Prize winners for this technique, the development of this technique, almost it fetched around 5 Nobel Prizes for developing this technique. Starting from Professor Rabi and Bach, Professor Ernst, Professor Utrich, and Professor Lauterboyer and Professor Mansfield. Variety of techniques they developed. So now, as an application, it is landed in the MRI. So that is nothing but the magnetic resonance image in every hospitals we are utilizing based on this technique concept what we are discussing today. So at least this will be more useful. And also out of all the spectroscopic technique, we have IR, UV, and other spectroscopic technique we have for structural characterization. And again, the NMR takes the lead to get a variety of information in the structural elucidation process. If you take IR, so at least you can just try to figure it out what kind of function group is there. But in the NMR, not only the proton, carbon, and you can have the stereochemistry and so on, a variety of techniques one can use. And in the structural elucidation, NMR spectroscopy takes the major percentage of the revealing the structural information. So let me start the concepts. That means the basic principles involved in the NMR technique. So that's what required for the students. At least they should understand what is the basic principles which is involved in the structural characterization of the NMR. And then there is another technique called a 2-dimensional NMR. I'm not going to touch upon those topics. And then it goes to the MRI image. So that is the evolution of the NMR spectroscopy from smaller molecular characterization to the images of the tissues and muscles available in our body. That's how the development took place recent. You can see 50 years or 60 years and 5-6 decades. This technique was developed before. So now within 5-6 decades, and it has got a very big importance for the benefit of mankind. So let us go to the principle. So the concepts, you can see as I said, it's become the most powerful tool, and a variety of nuclei, just given the proton, carbon, fluorine, phosphorus. These are most of the time, the scientists try to characterize some of the structures. And out of this, we just stick upon only the proton NMR. So we are not going to touch upon anything to explain the principles. And based on the periodic table variety of elements are available, then we know that whether all the elements are NMR active or not. So that is what the following information provides you. Which element in the periodic table is active, NMR active or NMR inactive, and so on. So these 3 lines, at least the student should remember for their benefit: odd atomic number, odd mass number. So the example is given here, proton or carbon 13 or exactly NMR active elements, and the spin quantum number values are given in the middle, and that is nothing but the half integer. So it is nothing but the half, 1/2 is the spin quantum number. When you have the elements having the odd atomic number and even mass number, having the spin quantum number as an integer, that means 1, 2, 3, and so on. You can see the example: a proton having 1 atomic number and 2 is the mass number, and nitrogen is 7 and 14. So you can have the odd atomic number and mass number, and these kind of elements are having the integer. That is also NMR active. The first 2 lines, whatever the elements from the periodic table falls in this category or NMR active. But only problem is whenever the element is having even atomic number, even mass number, the spin quantum number is 0. So that means what is the meaning for the 0. So then the totally inactive. So that's a major disadvantage for organic chemistry, which is available plenty in all the organic compounds. But you can see the C12 is totally inactive towards the NMR technique. And oxygen 16 is oxygen atomic number 8 and 16. So that's why both are even, and that's also totally inactive towards the NMR principles. So let us see that. So you can just see the next slide. So first, what we want to know is the spinning property of the nuclei to understand the principles behind the NMR technique. So just let me show the one small video just to explain this principle. Just let me play the one video. I hope you can see that as I shared my computer as such. So you can just see quickly. I have not selected the proton nucleus. You have only one proton in the middle. So I have just selected lithium atom, and you can just see that the atomic structure for the students all are familiar. You can just see the nucleus is spinning at the middle and the electrons are revolving. So that's what it is required to have. You just see that the nucleus is spinning. The many students are likely to forget. That means everyone remembers the electrons revolving around the nucleus. This sentence is repeated in the classes onwards, and always the students are very familiar. The electrons revolving around the nucleus, this sentence will be repeated, but the nucleus rotation is not at all known. So that means the nucleus is also rotating itself. This is a foremost basic principle for the NMR technique to explain. That's what required for the student to remember. I hope through this video at least they will be able to remember now onwards at least the nucleus spinning. So this is for lithium. The hydrogen is also the same way. So you can just extrapolate for the hydrogen. That is a basic, the small. You can just see that that is a basic fundamental atom to explain the principle from the first element of the periodic table. Now, so we just get familiar. The nuclear spinning is existing naturally. That means there is no external forces involved. That's why we believe in the nature still, and you can see that how that is a spinning, why electron is spinning. So all these things are natural concepts. So we have to build upon from the principles, from the basic fundamentals available from the nature. That's how the electron is spinning. The nucleus is also spinning on its own. So now the nucleus, if you just take it away, you just forget about the electron. Coming to the nucleus on the right hand side, and you can just see that when you consider the nucleus, so just only one proton nuclei. So that means I have come to the proton as the example to explain the principle. If you take the single proton, the nuclei possessing the proton, one proton having the positive charge. So we all know, we no need to have any kind of explanation for it. Then the charged proton, as we said for the lithium nucleus, for proton nuclei is also having self-spin by nature. Okay, so this is the fundamental concept. We have to build upon from there, whatever the further process or whatever the further principles built upon in this. Now, the proton is having the positive charge. When it spins, and there is a formation of magnetic field. Okay, this is again the physics principle. It is not a core chemistry principle, and at least this is a beginning of the era. The NMR technique is mainly developed by physicists. So that's why, because the physics principle only they understood much better than chemists. You can see the spinning charge generates the magnetic field, and the resulting spin magnet has the magnetic moment proportional to the spin. That means, we don't know what is the spinning speed. Then the spinning speed is very fast. Then you will have a magnetic moment also very high. That is not under our control now, because this is produced by the nature. Now you can just see that. So the nucleus is having charge, it spins, and then it develops the magnetic field automatically. The magnetic field, when it comes, then you get a dipolar nature, that is nothing but the north and south. So now you just see in this slide, next slide. Now the spinning proton having charges, we understood very well. Now it possesses the current. So that is a small amount of charge, still it is a current. Then when there is an electric field perpendicular to that, 90 degree to the electric field, you will be developing a magnetic field. So this is a fundamental basic physics principle. So we draw the principle from physics, and you can just see the magnetism is developed around this nucleus. Now your proton nuclei becomes the tiny magnet. That's why people will call it as the nuclei becomes the tiny magnet. So the magnet always possesses the north and south pole. So you can just see the situation. Now the spinning nuclei is considered as a tiny magnetic piece or magnetic pellet. So that's what it is happening in the principle. Now up to this, it is all natural process, nothing to do with us. Now the scientists are coming now onwards. They try to apply another magnetic field called external magnetic field. That means, powerful magnetic field. They try to expose towards the samples or proton nuclei. You can say the sample possesses the proton, so you are exposing the magnetic field towards this proton nuclei. Now you can consider the tiny magnetic piece is nothing but your proton nuclei. Now you just see that after applying the external magnetic field, the tiny nuclei is oriented in the two orientations. It gets automatically two possibilities, two theoretical possibilities. And now what is that? Opposite poles attracts and the same poles repulse. You can just see that south-south or south-north, that kind of polarity you get. Your dipolarity on the nuclear behavior. Now you can see in the external field, you can just classify into two types. So now you can see that opposite poles attracts or having the lower energy, and now like poles or opposes each other. Automatically you need to have a higher energy with respect to the proton nuclei. So that means you need to have a higher energy state and lower energy. So you just coming to the two different energy states, and that's what it is given. You can see this is applied field normally denoted in terms of V0. In many books you can see that. Now you just see the spinning nuclei with positive charge on the left, and you can just see the orientation. If you consider this is a anti-clockwise, it spins. Then if you just apply the magnetic field, it gets two orientations. Now you can see the opposite poles attract spins. Now the like poles opposes. Now the nuclei gets inverted. That means if the north pole is on the top, in the second picture the north pole should be at the bottom. So now you can just see that it gets inverted. Now you can see the spinning also gets inverted. That's what the student should be able to understand. Not only the nuclei inverts, your spinning also rotates on the opposite direction as indicated in the arrow mark. The magnetic field generated by the nucleus by the spin of plus half, opposite direction, that is by a nucleus of another minus half. It is actually the two different energy states. We call it as a lower energy and higher energy. And these two energy states sometimes called as alpha spin and then beta spin, or plus half or minus half. It's a different notations meaning the same, the lower energy and higher energy. Now let us consider. So far we are considering the single proton. Now you just consider, around here it is shown some 7 protons. When there is no external magnetic field, now you can see the orientations of these nuclei or now if you apply the B0 on the next picture, now you can see in presence of the magnetic field, all these nuclei are getting oriented in a particular fashion. So what is that? Aligning to the B0, that means this is external field, and you can see the aligning to that 1, 2, 3, 4 nuclei. You can just count it. 4 nuclei are aligning, and you can see other possibility you can oppose 1, 2, 3. So you can just see that 3 nuclei are trying to oppose it. That means you get 2 classifications, and whatever aligning should have a lesser energy, whatever the opposing nuclei should have a more energy. So that's what now you can just see. So these nuclei, whatever the charged spinning proton nuclei, it possessing the circular movement in the presence of the applied field. It is called the precision. So you can see the circle, whatever it is shown, that is an orbit, precisional orbit, which is shown here also, the dotted line. You can see the nucleus is here only, but whatever the rotation is just given in the orbit, that is nothing but your precisional orbit. When it spins, and always in any spinning object, you can get some kind of a frequency with respect to the time, and that is nothing but Larmor frequency in the case of proton nuclei, or you can symbol is omega 0. The angular frequency of the precision is related to the external magnetic field strength B0. The gyromagnetic ratio is the constant, and you can see the Larmor frequency. If this is a constant, gyromagnetic ratio is a constant. Now left hand side you have a Larmor frequency, right hand side you have a B0, that is nothing but the applied magnetic field by scientist. Now you can just see that. So that if you increase the B0, that means I can increase the magnetic field strength towards this proton nuclei. It is possible artificially to increase it. Now what you will get Larmor frequency. That means the frequency, the spinning frequency of the nucleus, I can increase automatically. So that's why from the natural process. Natural process possesses some spinning speed. Now artificially we can increase the spinning speed with the help of the magnetic field. That's why external magnetic field is always required in any orbit. Now we see this nucleus. The spinning nucleus are now you magnetic field given properly. Given the spinning see the rotates. So then if the spinning stops, now you can just there you can get for your proton nuclei, and you can see the charge on the top is the north pole, and consider south is the bottom portion. This tiny magnetic pellet, so if you are putting in the applied magnetic B0, if you are increasing the frequency, that means the precisional orbit, you can increase the speed very fast when you increase the B0. That is a well understood concept after this. Now you can just see that in the next slide, so which we have given, we are talking about the proton nuclei, which is having the odd atomic number and odd mass number. The spin quantum number is exactly half, and that's why you just ignore the other possibilities. And considering to this portion, now you can just see the I equal to half. Whenever you can have the I equal to half, you get a number of states, energy states. What you get is 2I plus 1 formula. So that's 2 into half plus 1. So you will get 1 plus 1 equal to 2 energy states. That is what given as a plus half and minus half. And now your principle understood, you can understood better way, and you can just see the lower energy alpha spinning states gets the lower energy, and your beta spinning states gets the higher energy that can be represented as a minus half. So when you get these two energy states of the nuclei, proton nuclei, this is in the absence of magnetic field. Now in the presence of magnetic field, you are able to get two energy levels. That is explained in this slide nicely. So when you have a nuclei, proton nuclei, so that means at this point B0 is 0. That means there is no my external applied field is provided in this case. Now slowly you are moving towards the right, and you can just see the value of V0. That means the strength of the magnetic field in terms of Tesla. So the magnetic field unit is always a Tesla. So you can just increase the magnetic field from the left to right. So you can just towards the nuclei, you can keep increasing. There is a separation of the lower energy state and the higher energy state. Always you can observe. When the V0 is almost how much you can generate, artificially, experimentally you have to prove it. So what you can get is, compared to the lower B0 value, higher B0, you get a very good separation in between the two spin states of alpha and beta. So that's what it is given. The presence of the external magnetic field will cause the diverse between the higher and lower energy spin states. As the intensity of the external field increases, the separation of the energy widen between the spinning states keep on widening. So that means the lower energy and higher energy state, so you can always increase artificially with the help of the external magnetic field. Now this picture it is given. So in terms of value of the magnetic field, you can see, for example, 1.41 Tesla. So you will be getting 60 megahertz of the spinning speed of the proton nuclei. For 2.3 Tesla, that is a V0 value, magnetic field strength. Now you will get the precessional frequency or Larmor frequency, you can say, for the proton nuclei that can spin 100 megahertz speed. So that means the students can understand what is megahertz is nothing but the 10 to the power of 6 hertz. That means 100 into 10 to the power of 6. What is the answer comes? That is many zeros will come. So you have to write and check that many times within a second. The proton nuclei precess within a given 1 second time. So that is nothing but your frequency. Now you can just see, I'm just increasing 11.7 Tesla, and you get 500 megahertz is the spinning speed of the nuclei. So the nuclei is same, proton nuclei is the same, and you can see the spin, the natural spin is very less. Now artificially this nuclear spinning you can increase with the help of V0. Now this helps the energy gap. Now you get two different spin states of alpha and beta, lower energy and higher energy. Now you just see in the lower energy there are 6 aromers, 6 proton nuclei. Now you can just see that on the top you have a 5 nuclei. So that means it's always based on your Boltzmann distribution. The population of the lower energy state will be always little higher than the higher energy state. That is always, it should be there. So now it will not be rules. You can't get excited state or higher energy state will not have a more populated than the lower energy state. That's not possible based on the Boltzmann distribution, which normally students study in the physical chemistry area. Now you can just see that the strength of the signal depends on the population difference between the alpha and beta spins. Now what we can do, so you get two energy states. Some of the proton nuclei can populated on the lower energy. Some of the nuclei can be populated on the excited state with the help of applied magnetic field, that is a B0. When it is no applied magnetic field, all the nuclei is having single state. There is no difference between any nuclei, any proton nuclei. Even the compound possessing the 10 or 20 protons, all will be having the same state. Otherwise, there is no difference in it. You can see if you are applying your radio frequency, because what is done in the NMR frequency, whatever you are getting 100 megahertz or 500 megahertz, whatever the frequency you are measuring for the nuclei, which is available from the electromagnetic radiation, corresponds to the 100 megahertz and 500 megahertz that is available in your radio frequency range only. It is not in the IR, it is not in the UV region, it is not in the microwave region, and so on. So that's why, so in the electromagnetic spectrum, all of us is very familiar. And the lower energy radiation is nothing but the radio frequency energy. That frequency range, if you take, it will be, you can see the 100 megahertz or kilohertz, starting from kilohertz, some of the radio frequency waves are there, then completely falls into the category of megahertz frequency. So that radio frequency, scientists are trying to expose or irradiate towards this lower energy nuclei, then trying to make the resonance. That means, if this is a 500 megahertz spinning speed, I can generate, now it is electronically, technology is available, you can synthesize the radio frequency energy of 500 megahertz. It is like, your musical synthesizers and so on. It's all placed based on the frequency of the waves. And based on that, you can synthesize the 500 megahertz radio wave towards this 500 megahertz spinning nuclei. That means, when the frequency is same, the energy can be transferred from radio frequency to the nuclei. When the energy is absorbed by this nuclei, immediately it gets excited to the higher energy and trying to oppose magnetic field of B0 automatically. Okay, so that's the thing with the radio frequency, definitely helps in this case. And now you just leave it for some time, that it's not exposed. Radio frequency is not given continuously, only for particular duration you can irradiate this nuclei. Then you have to stop the pulse. That means, the signal is given in terms of pulse. That means, it is not a continuous irradiation, it is a pulse signal is exposed towards the nuclei. Now, if any student is asking that, if this condition is upper and lower energy states, the number of nuclei is equal, then nothing will happen. Because if you are having, if you are providing some particular condition, there are 6 nuclei in the lower energy level, another 6 nuclei on the higher energy level. If the population of the lower energy and the higher energy states are same, then you will not be able to get any kind of signals in NMR output. That is called, this process is called saturation. Then after irradiating the radio frequency signal towards the nuclei, now you just stop the radio frequency, then you allow the excited nuclei to relax automatically to emit the whatever the radio frequency absorbed by the corresponding nuclei will be emitted automatically, and electronically the equipment captures the radio frequency emitted from the sample, and then it records the FID, free induction decay. This picture is nothing but the free induction decay, that is nothing but the FID. Now computer calculates the FID, converts into the frequency. Whatever it is, time domain data, that is FID is nothing but the time domain data. So that means with respect to time, whatever the energy absorbed, so it is recorded in the instrument. Now this time domain data is converted into the frequency domain data, that is nothing but your Fourier transformation based on the mathematical integration equations. It is done by the system automatically. We no need to do anything much on the student side. Now you can just see the excited nuclei, what happens when you stop the radio frequency. So the excited state, it cannot stay on the higher energy level always. So it has to dissipate the energy. It just relaxing itself to come into the ground state. That is nothing but to have 2 types of relaxation effects. It's relaxation, and you will be calling as a dipolar coupling or a dipolar state. You can see spin lattice. That means spin lattice relaxation means whatever it will be dissipated to the environment. Whether maybe the solvent molecule or nearby some other proton molecules will be there. So you can say that the energy will be transferred in that way. And otherwise, so spin relaxation, Now the excited spin state will come down automatically by emitting the radio frequency. In this process, this spin relaxation is called scalar coupling. So you can see through the scalar coupling. So you can just say, the spin lattice is nothing but the dipolar coupling. Spin relaxation will be the scalar coupling. These two relaxation effects are there, and these two states are denoted as a T1 and T2. And you can see that based on the T1 relaxation and the T2 relaxation, you will be trying to measure the output, what it is emitted with the radio frequency. Based on that types of proton, you can try to measure experimentally. So now let us briefly, after going through the concept, and let us briefly the experiment. So this is just a view of the NMR experiment. So this is a block diagram what you are seeing, and this is a sample tube where the sample to be analyzed, and you can see surrounded by that magnet is available. So that means you need to have keep the sample in between the magnet. That means the magnetic field, external magnetic field of B0 is must to irradiate towards the sample. Thereby, the proton nuclei will try to precess. The Larmor frequency will be high, then radio frequency resonance will take place, and the excitation process will take place. And then your radio frequency transmitter will be there to supply that, and the radio frequency receiver also will be there for the receiving the radio frequency waves. Now you just see the sample preparation. So you have a 6 or 7 inch length of a glass tube. So where 5 mm diameter of the tube, you can just fill the sample dissolved in a solvent which is given, and just so that no oxygen will be there. So that's the paramagnetic, and come to the paramagnetic a little later. And anywhere between 1 to 5 milligram of the sample is enough to record for the any given proton NMR. It is a 1 milligram sample or 2 milligrams. Such a very less quantity is enough. And this is another experimental background, theoretical background. You can say that whenever you do the proton NMR experiments, and this is nothing but the pulse signal, one pulse signal. So that means one single NMR pulse signal. How it is given, so you can see the total duration of the time is 2 seconds with respect to time, and everything is recorded. Now you can just see when you start the sample, and there will be a delay time. So that means the sample preparation, nothing will be done. So there will be a sample will be quiet. After that, after a second or so, now you can just see the radio frequency signal will be irradiated towards the sample for the duration of microseconds. Sorry, this is it should be a microsecond. So now you just you can see 5 microseconds. See, we know that 1 second is how much time is, and millisecond is 1,000 of it, and the microsecond is nothing but the 10 to the power of 6 seconds. So you can just see how shorter time. So you can just provide the pulse, radio frequency pulse towards the sample, and leave it to 0. Again, nothing. Only the excited state nuclei will come to the ground state during this time. So that is nothing but your acquisition time. So where you can receive your radio frequency, that is emitted from the sample outside. So that will be captured by the electronics automatically to provide the one single. Then the same sequence is repeated once again and again. It is repeated with the small quantity of the sample. You get 1 proton spectra out of it. Then 100 scanning you can do it. So people will call it as a scanning while recording. That means 1 radio frequency signal is sent. 100 radio frequency signal will be sent for the particular duration, and you will be collecting hundreds of proton NMR spectra. Then your time domain collected, time domain data will be converted into frequency domain data as a outside. So this is just a equipment diagram which is available in our department. So let us move to the third topic, is a chemical shift. The horizontal scale of the x-axis of your proton NMR is nothing but the chemical shift, which is always denoted in the parts per million. That means x-axis is nothing but the frequency. You can see that to avoid this frequency in the x-axis, instrument to instrument, different magnetic field will be used. The x-axis will be varying. That is why independent of the frequency, you need to provide the output from the NMR machine. That is all about to provide the chemical shift. That is a man-made formula by keeping the reference as the tetramethylsilane, you try to record the other signals as you observe. Then what are the importance of the tetramethylsilane? All these things are given, so I hope you can go through easily. Now you can see tetramethylsilane is calibrated purposefully, keeping at 0. It is not that TMS is coming at 0. It is actually we are keeping TMS as 0. Then other samples, no proton peaks will appear on the left to it. Normally, tetramethylsilane is provided in this shielded region. Now, if you are coming on the left-hand side of your proton spectra, it's not nothing but your downfielded region. And you can see some of the peaks likely to come right-hand side of the 0. Some of the peaks will come above 10 also. Okay, that possibility is also existing. So here what we say, the x-axis is a chemical shift denoted in delta, and parts per million is the unit. And relative to the TMS, relative to the standard, universally it is taken as a standard. Then relative to the standard, so whatever the samples, unknown samples you record, you try to report as such in the literature values, whatever it is observed. So that means, in reality, the x-axis in original, it is not at all a chemical shift value. It is behind that x-axis, your radio frequency is there behind the x-axis. That means, radio frequency when you are recording in the 100 MHz machine will be different. 500 MHz machine will be entirely different. So the data will be wrong whenever we give the things. Okay, so now you just see common NMR solvents. What are the solvents you can try to take? All organic solvents, whatever you feel. So only the deuterated, that means proton should not be there. Only the deuterated samples you can have it. Now you just see out of these solvents, the chloroform is the cheapest one. Otherwise, isotopic labeling is done for all these samples and become a very expensive process when you purchase in the market. So the chloroform D is the cheapest one, most widely used organic solvent for your proton NMR spectrum. Now, after the spectra, so what kind of output you get as a, based on the concept, based on the equipment, what you are using, the output, what it comes is nothing but the number of signals, position, intensity or integration of this signal. Then there is a multiplicity. It is called spin-spin multiplicity of the signals. So now you can just see that a number of signals for a given compound, how you can get it. So go to the example directly. So you can see dimethyl ether, simple compound is given for the explanation. If you take a dimethyl ether, all the 6 protons, 2 methyl groups are same environment because it is attached to the oxygen. This methyl is also attached to the oxygen. Only one type of proton existing, you are likely to get only one signal. If you take this third example, so you can see the methyl ethyl ether, you can have a one signal for methyl, another signal for CH2, third signal for the CH3. So all the 3 types of protons are available. Thereby, you are likely to get 3 signals in the NMR output. Now you can just take this number of signals, cyclohexane, so you are going to get only 1. If you take a paraxylene, aromatic, all the 4 protons, 1 signal, 2 methyl groups, it should be another signal. So it should be 2 different signals you are likely to get. So this is a basic output you can theoretically also predict, and experimentally you will get. Second point, the position of the signal. So that means we showed the scale of 0 to 10 ppm in the chemical shift scale. Now where the peak will appear for the given compound, for the unknown compound, and so on. Now you just see the nucleus. So far we discussed without considering the electronic cloud surrounded by the nucleus. Whatever the concept we explained with respect to only the nucleus. Now, in reality, you can see that the nucleus is in between the electronic cloud. So whatever the blue colored indicated is nothing but the electronic cloud. It is like a blanket. Now you can see the nucleus at the peak. Your electron density is completely covered. That means the molecule to molecule, if the 10 or 12 protons are available in a given compound, then these compounds are electronically affected automatically. So that's why the nucleus is shielded. So now you can just see that the nucleus is shielded. Whenever the electronic cloud is surrounded by the nucleus in a thick manner. You can just see that 0 to 15 ppm scale is given here. Now approximately you can place the class of compounds, organic compounds. Now all aliphatic compounds around 1 ppm, alcohols and protons of ketones and something like that. You can see alpha to the ketone. That means acetyl groups. You can say that COCH3. That means methyl group, acetyl methyl group around 2.5 or 3 ppm. Olefin comes around 5 ppm. Aromatics comes around 7 ppm. Aldehydes, the acids goes above 10 ppm and so on. This is a gross classification. It is there is a, at least one can make it output in this scale without any much disturbance. But you have to go in deep to characterize further. But at least at these levels, the student should know the range of protons and with the chemical shift, the respective chemical shift values. Now these position of the signals gets affected. It is not that when we say that here you can see one particular compound. If you take a methane, it's a gas, so it's very difficult to record, and you can see right hand side of the TMS comes. It is normally cannot be a routine manner, we can't do it. But if you take a methyl chloride, 1 chlorine attached to 3 ppm, and dichloromethane 5.3 ppm, chloroform 7.3 ppm. You can see all are same carbon, and only the number of hydrogens are 1, 2, 3, but the number of chlorines keep increasing, the electronegativity increases. You can see that slowly the protons are placed in the de-shielded region. So that means here it is a shielded, and then slowly the electron withdrawing character of the chlorine is de-shielding the proton electronic cloud, the blue cloud, electronic cloud, whatever I showed in the previous slide, and slowly withdrawn due to the 3 chlorine atom for chloroform. You can see 7.3 ppm it appears. The similar example, one more example I have given at the bottom with the bromine. Now you can see the temperature. Yes, temperature do affect your proton NMR experiment. You can see methanol, simple methanol provides 2 peaks at room temperature 30 degree. Now if you go down to -45, the same methanol, you can see the multiplicity of a doublet. I mean 3.3 for methyl group appears singlet, but here it is a low temperature doublet. Now you can see the 4-line spectra quartet for the alcoholic proton around 5.5. So the multiplicity pattern entirely differs with respect to the temperature and the solvent. So that means if you are taking a chemical and you are recording the proton NMR in CDCl3, I told this is the most common solvent to record the proton NMR. You get a 3.4 and 1.1 for methanol peak. It is a very simple compound. It is indicated. If you take DMSO, you can see 3.16 and 4.1 is the value. So that means the chemical shift value or ppm value or delta value differs with respect to the solvent. At least you should know, because there is a kind of interactions like a van der Waals force, or you can see hydrogen bonding mainly compared to DMSO and CDCl3. So polar solvents, non-polar solvents, it all differs properties. So that's why whenever you report the NMR data, you need to provide the name of the solvent, particularly before the data itself. Then the concentration, 1 molar concentration to 0.001 molar concentration. Again, you can see the particular proton where the hydroxy group, you can see that it keeps shifting in different locations based on the concentration, because the concentration, hydrogen bonding affects based on the concentration, which we all know whenever we study the hydrogen bonding property, and based on that, the concentration is also affecting the chemical shift value which is given. So now that is why the OH peak and the SH peak and the NH, these are easily replaceable and easily involving the hydrogen bonding like a donor acceptor properties and so on. And that's why it affects based on the concentration, temperature, solvent. And to verify this, always you need to do the exchange experiments with the D2O. That means OH to OD, you have to do deuterium exchange experiments. Then you can just see that to confirm these peaks. Otherwise you can't give. Alkyne comes around 1 ppm or 1.5 ppm, aromatic comes around 7 ppm, we said. But for this kind of easily exchangeable proton, you don't have any chemical shift, fixed chemical shift value. That should be done by experimentally only. Now you can just see the chemical shift value of the olefinic proton, so the aromatic proton, vinylic proton, acetylenic proton, all these colored protons are attached. The value is not the same. You can just see getting differed around 2.5 to 8 ppm. So that means, all are olefinic protons. We feel that it is a commonly placed in one particular region of the x-axis and the chemical shift value, but it differs particularly based on these groups. Then people identify the reason for it. It is called, the anisotropic effect. This is nothing but your anisotropic effect involved. What is that anisotropic effect? So you just take an example of a benzene ring. You have an electronic cloud on the above and bottom. So we all know the structure of benzene. When you apply the magnetic field, so you generated the magnetism, as we discussed for the theory. Now this electronic cloud, again the charged electronic cloud, that generates the secondary magnetic field as shown in the green arrow mark as the secondary magnetic field. This magnetic field creates the two environment at the middle as a diamagnetic. On the parallel to the B0 is nothing but the paramagnetic, and the middle portion it gets opposing the B0, so it is a diamagnetic region. So that's why whenever the proton falls in this paramagnetic region, it's getting de-shielded. Whenever the proton falls in the diamagnetic region, gets in the shielded towards the TMS side, towards the right hand side, you will be getting the chemical shift value. So now if you take the vinylic proton comes around 5.6, you can see it is not exactly in the paramagnetic region as it involved in the aromatic ring in the previous slide. Now this is a little away from the paramagnetic. You can see around 5.6. Now in the case of acetylene, you can see the triple bond is having the circulation of the electron in this direction horizontally. Now vertically you are able to generate the magnetic field, 90 degree to the electric field, as we said. Now you can see the acetylenic proton is exactly falls in the diamagnetic region where the magnetic field opposes the B0. So that's why this proton location exactly getting shielded. That's why you get around 2.5 ppm. The aldehyde proton around 9 to 10. So it's actually exactly falls in the paramagnetic region. So not like aromatic. So but exactly falls in the paramagnetic region. That's why completely de-shielded around 10 ppm or sometimes 11 ppm also it goes for the aldehyde proton. So the next third topic in this is nothing but your integration. So integration, nothing but the peak area, whatever the output has come, you can just measure the number of protons. So here it is a 3 proton, here it is a 9 proton for the tertiary butyl ester, tertiary butyl methyl ester. What is the example it is given here? So you can integrate, or in the vertical line, people used to calculate olden days, but now the computer calculates the peak area nicely at the bottom. Students no need to do much on that. So this is another example with the multiplicity pattern for the methyl acetate to find the integration on that. So let us move to the last title, the coupling constant, or the fourth topic, nothing but your spin-spin coupling. This itself a big chapter on the NMR spectroscopy. Now let us see the spin-spin coupling, what it happens. Whenever the proton, when you are observing, so when you are having the nearby proton, it, we say it is a tiny magnet. So that means, if you are keeping a nearby another magnetic piece, there will be a force through the chemical bond. There is a kind of interaction, always, trying to observable. So if you are putting on the left-hand side proton and the right-hand side proton can be communicated through these 3 chemical bonds. So this provides the multiplicity. For example, this proton gets the doublet because of the nearby 1 proton. Now you get the coupling constant value in between the 2 lines if it is a doublet. Coupling constant that is always given in terms of heads, and this coupling constant is fortunately independent of the magnetic field B0, because there is no role of the B0 in this case. So that's why it is always a constant value, you should get it. So now you just, for example, HA, HB, 2 vicinal protons are given, and you get a doublet for HA and another doublet for HB. So again, theory is there for this. What is the theory behind that? So if you are observing the HA proton, your HB proton, this red colored arrow mark is not meant for the HB proton. now you can see the Hb proton is, one is aligned to the magnetic field, another one is opposing to the magnetic field. Then you get a two possibilities. Out of these two possibilities, you just record the two different lines for the observing HA proton. So HA is coupled to 2b in two different manner, that is anti-parallel or parallel manner. That's why you get 1:1 doublet out of it. So more coupling it comes when you have two protons and then you get a triplet on the Hb, and Hb gets the doublet whenever you see the nearby one proton. And there is a common formula called, everyone knows, it's a n+1 formula. That is the exact formula is nothing but the 2ni+1 is the formula to substitute your I equal to half value for the proton. Thereby you get the multiplicity nicely, and in between these two lines nothing but your coupling constant, and for a triplet you can get one single coupling constant, and a doublet also you get a single coupling constant. So now you can see for triplet also, you can theoretically you can predict why I'm getting three lines with the different intensities, 1:2:1. There is an exact reason for it and a theoretical things. So Hb, two Hb protons, and you have to take two Hb protons are aligned, two Hb protons are opposed, and the other two possibilities, one is opposed, second one is opposed, first one is opposed, second one is aligned, first one is aligned, second one is opposed. So in that way, you just make four different combinations you get out of these two protons with the two spin states. You will be getting four possibilities, and the energy level wise, as I said, the parallel to the B0 is always having the lesser. These two are having the equal energy, and then opposing to the B0 gets the higher energy. That's why you get placed in the three different chemical shift values in the x-axis of your NMR spectrum. So similarly, one can go for the quartet and quintet and so on. Now you can just see for that Pascal triangle provides the exactly one can get the intensity of the signal. The formula is nothing but the 2ni+1. You should remember, you should not remember the n+1 rule. It is actually better to know that a complete formula 2ni+1, where n is the number of protons. So that's a thing. So now coupling, what is coupling constant after getting this multiplicity? So you can see the distance of the peaks in the multiplet and measured in terms of heads. As I said, not completely independent of the magnetic field. Whatever the equipment you use, the coupling constant value is always same. Adjacent group of protons that split each other to provide the coupling constant multiplicity value. And these are some class of classification of the protons. For example, aromatic ring, orthoproton having coupling constant value of 8 heads, metaproton having 2 heads, and paraproton will not have a coupling constant at all, where there is a number of chemical bond distance goes to 5. And vicinal proton, there is a reason for it, and the cis and trans, there is a coupling constant value. Based on that, one can identify whether obtained product is whether it is a cis or not, and so on. So for vicinal proton, there is called Corpus equation. So that means you can't fix exactly 7 heads. It is not correct. So there is a range of coupling constant value as shown in the graph. In the x-axis is the dihedral angle between these two vicinal protons, and then the y-axis is nothing but your coupling constant value. So now it around 9 heads, you can see 9-10 heads onwards. When it is a dihedral angle 90 degree, you get there is no coupling at all, and again up to 180 degree, so you get 9 heads or 10 heads coupling constant value. So in between the dihedral angle, you get in between coupling constant. So this equation and the formula should be known for the Corpus equation for the vicinal proton to identify the coupling constant value. And this is a first order coupling, so always only one coupling constant irrespective of the many peaks. You can see the in between the gaps, peak number 1 and 2, peak number 3 and 4, always you try to have the single coupling constant value out of it. So that means the uniformity will be there. So whenever you measure, for example, coupling constant value between the first peak and second peak, and the second and third peak for a triplet, it will be the exactly same. That is nothing but your first order spectra predicted by your Pascal triangle. So there won't be any problem. So whenever you get first order spectra, you need to have satisfy the condition. difference between the chemical shift value should be the 5 times of the coupling constant value. I mean, divided by the coupling constant should be more than 5 times should be there. All your first order spectra will be centrosymmetric, as we have seen in the previous slide. The multiplicity based on the n+1 rule whenever you have a I equal to half. Let me see that Popel notation just briefly. So a few slides to go to complete. Whenever you have a first order spectra, the NMR spectra analysis is much simpler. And when you have a first order spectra itself, A, B, A, X, some different patterns proposed by Popel, that is called Popel notation. It is given. So these alphabets I give, sometimes people call it as a AB quadrant and AX, AB2, AMX pattern, and different types of patterns are given based on the alphabets which is used in the English alphabet of A to Z. There is a distance between the alphabets. So based on that, whenever the vicinal proton is very close, you can say that AB pattern. When proton is a little away chemical shift value, you can always give the AX pattern. So similar to that, one or two examples. Now you can see the AB system. So that means 2 doublets nearer to it. And now this is a first order spectra. So now the condition of difference in chemical shift value divided by coupling constant value provides more than 15, equal to 15. There is no problem. You get a first order. If this ratio is going down, you see it looks like a quadrat, but this is not a quadrat. There is a 2 doublets. Now you can just see the ratio between the chemical shift and the coupling constant goes down and down. You result in these are called the second order spectra. That means you can't predict it directly. So that means the second order spectra comes as an output from the NMR spectrometer. Then the real complication for the student's analysis becomes the troublesome one. This is another example, AB2 system. That means B2 provides the B2. You can see the triplet will form, and A will give you doublet, and you can see 1 doublet and triplet. Now you can see the ratio goes down, and the complete pattern will be completely changed. It is very difficult to analyze. It is nothing but your second order spectra. NMR spectra analysis becomes very, very difficult. And this is one example for AMX pattern. Now you just see the AMX pattern. So you have a 1, 2, 3 proton. These 3 protons are called AMX pattern. In the chemical shift value, it is almost closer, and you can see the multiplicity is one is a doublet, another is called a double doublet. This next version of the multiplicity, and then another proton comes in the double doublet. So doublet. Now you can see the double doublet comes because of this proton couples with the neighboring proton is a doublet, and this proton couples with the another meta proton gets another doublet. You get a 2 coupling constant value. This is a higher version, higher order of coupling constant multiplicity topic. So okay, this is a little difficult to understand for the fundamental students like undergraduation but at least the students should be able to try to predict what is a singlet, doublet, triplet are very well known. If you are going higher order, then double doublet, and even the 3 alphabets also will be together. That is much more complex for the students unless they practice.
So another 5 minutes.
Yeah. So this is a simplification of the second order spectra when resulting in the complexation. How to characterize? This becomes the difficulty for the students level. So you have the different techniques. High field strength. That means B0 should be more. That means you have to move to the higher level of equipment, solvent effect, deuterium exchange, spin-spin decoupling, that is a double irradiation experiments, lanthanide shift reagents or chiral resolving agents, NOE effect, variable temperature and all. So you have a variety of techniques you can use to simplify the second order spectra. So I'm not going to give you any detail on this topic based on the timings, and let us have only very few examples, and you know that this is a basic your ethanol spectra, whatever you get output in the NMR spectrum with a triplet for your methyl group, and CH2 gets the quadrat. It's a very simple compounds to know that. And again, ethyl bromide as a x-axis, and then you get a multiplicity. You get a coupling constant value for this group, coupling constant value for the another triplet, as it is a first order spectrum. So the first order spectra is very easy for students, and you can just see this is just a propane spectrum. So you can see beautifully the triplet for the A type of proton, that is for the methyl due to the methylene proton. You can see the methyl groups are 6 protons are available, and you get in the middle CH2 gets reflected as a septet. You can have a 7 peaks are available for the septet. When the complication comes, so you can see the nitropropane. So it's a very, it looks like a nitropropane is a very simple compound. You have a 3 types of protons, and every proton, for example, A is a triplet, which is given here. B is looking for the 5 protons. It looks like a 6 peak spectra for B, and C is again triplet for the nitropropane. So you can see the multiplicity for the expanded spectra. So here it is not so visible, but one can expand and see the multiplicity exactly to measure the coupling constant in between the gaps. That's how you can just try to report on the compounds. So I hope with this, let me complete the topic, the overview what I have given, more on the concepts and less on the examples, on the simple examples. So I must thank the Chemical Research Society of India for creating this awareness, at least among the students and colleges, to by keeping the November 2 to 7 as the National Chemistry Week. Thank you for your kind patience. Thank you very much.
Thank you so much, sir. Over to Raja. So any questions from the student side? So Raja, you are a moderator, right? You can read the questions of the students so that all can answer.
Yes.
We'll pick up some questions.
Yes, sir. Students, do you have any questions and you can ask now? Yes, sir.
One student asked the question.
Yes, sir. Yes, sir.
Mr. Kari asked me this question. Thank you very much, sir, for your wonderful presentation. Tetramethyl is a reference. Is there any other reference?
Reference? You mean the other references?
Yes, sir. Yes, sir.
No, there is no other reference available. Only the tetramethylsilane, the standard reference universally. If you want to have any other reference, that is a new problem for the research. No, it is very difficult, because so far no one could be able to get other reference material by all the properties. It should be inert, and it should be a singlet. Multiplicity should not be given. Many reasons. Whatever you get output for the TMS, and you don't have any other reference for the proton NMR. Even for the carbon NMR, also the same reference is used.
Another student asked a question. So in conventional NMR technique, the sample should be a homogeneous solution. But in MRI technique, the sample is not. How can we overcome this problem, sir?
No, sample is a...
So in NMR technique, the sample should be a homogeneous one.
Yeah.
In MRI technique, the sample is not in homogeneous. So what technology is used to overcome this problem, sir?
No, that is, you see there, it is a aqueous medium is the solvent. It is not the deuterated solvents or anything, whatever we do for the laboratory purpose. And all muscles and bones, whatever it is there, so that provides the image. That's called 3-dimensional NMR. That is altogether different topic to discuss on it. Okay, that's called imaging. So whatever we get as spectral output, there you get a imaging.
Okay, sir. Okay, Mr. Madhavan has asked this question. After excitation, the excited state spin is same or different?
Can keep this as the last question? Yeah.
No, excited spin state is. No, excited spin is the higher energy level, no?
Yes, sir.
That is a higher energy level. So automatically it relaxes into the ground state. by emitting the radio frequency.
Okay, sir. Okay, thank you, sir. On behalf of organizing committee, we wholeheartedly thank our research person for his wonderful presentation of NMR spectra. Thank you very much, sir.
Okay, thank you, thanks a lot.
So we have just visualized the nuclear magnetic resonance pattern by Professor S. Muthuswamy sir, who lucidly coupled all of us through his magnetic power. So thank you, sir. In this occasion, I welcome the senior Professor Palaniandava sir to this wonderful lecture program. Welcome you, sir. Next, I feel happy to invite my beloved colleague, Dr. M. Ganapathy sir, Assistant Professor of Chemistry, Vivekananda College, to chair this A-Session 2 by Professor P. Tilaga sir, IIC Bangalore. Welcome you, sir.
Yes, can you hear me, Raja?
Yes, sir.
Yes, thank you. Good afternoon to all of you. I can see that Dr. Palaniandava is here. I am extremely happy to welcome you, sir. Dr. Palaniandava is a well-known scientist in Tamil Nadu, India, and also internationally for so many years in the area of bioinorganic chemistry. I remember him for a long time because he is the person who arranging so many meetings like this in Down Arts College. So once again, I welcome you, sir. Right. On behalf of our department, I request you to encourage us also the same fashion, sir. Right. Now, I'm very honored to welcome Dr. Tilagar. He was born in Perikottapalayam, Kodur district, Tamil Nadu. He obtained his BS degree from Tagore Arts College and MSc from Pondicherry Central University. After that, he moved IIT Kanpur for his PhD. He did his PhD under the guidance of Professor Chandrasekar. Then he did his postdoc in University of Rutgers with Professor Frieder Jockler, USA. In the year 2009, he joined Indian Institute of Science as a faculty member in IPC department, where I have been for 2 years. I think now he is using the lab of Professor Dr. Krishnamurthy. His current research areas are here: application-induced emissive materials, solid-state emission, sensors, enzyme inhibitors, stimuli-responsive materials. It is very important to mention that he has got close to 2,500 citations, and his Hutch index is 28 and his I-10 index is 52. So now I would like, also he is a member of internationally advisory editorial board and editorial in so many reputed journals such as Thought and Transaction, Journal of Organometallic Chemistry, and Journal of Aggregation, so on. Now I would like to invite such an eminent personality to talk with us and motivate the student. Please welcome, sir. Please, you can take a session. Thank you, sir. The time is yours.
So, can you unmute your mic, Clarana? Mute your mic.
Is my slides getting shared?
Yes.
Okay.
Yeah. Make it full screen, please. Not full screen.
Still? Is it okay?
Yes. Yes, fine. Yeah, great.
Thank you. At the outset, let me thank the CRSI for doing this wonderful job, creating awareness among students and younger colleagues. And also, I would like to thank Mr. Professor Mayil Murugan for taking the initiative and spreading the news to all the students. Also, I am very much happy to see Professor Palaniandava after a very long time, and also Professor Muthuswamy. And also, I would like to thank Professor Muthuswamy for a beautiful lecture for the young minds about NMR. I really enjoyed your lecture. Thank you, sir. And today I didn't know that these audience are so heterogeneous. I prepared my lecture a bit technical, but after seeing the audience, I modified it to a bit general. Okay, I hope you guys would enjoy it. I titled my talk as boron-based materials and medicinal molecules. So before getting to the details of technical details of this topic, I would like to very briefly mention about why boron and what is special about boron and what one can do with boron. Okay, so I believe all of you remember your periodic table. So could you please recollect what is the position of this element boron in the periodic table? Well, it's the 5th element in the periodic table. Okay, so as a boron chemist, I would like to see the periodic table like this, right? The hydrogen is here, helium, lithium, beryllium, and boron, the 5th element in the periodic table. Like the boron, the chemistry of boron dominates the other elements. I believe at the end of my talk, you will agree with my proposition. Okay, let's start. What is special about boron? Okay, boron is a metalloid, it's not a metal, with a symbol B and atomic number 5. The word boron was coined from borax, the mineral from which it was isolated. Okay. The name boron was proposed by Sir Humphrey Davy to indicate the source of the element and its similarity, the chemical similarity to carbon. Okay. The color of boron is also black and the carbon color also black. And also if we compare the chemistry, the boron chemistry more resembles the carbon chemistry rather than its aluminum and other elements. That's why they named it as boron, borax plus carbon boron. Okay, the electronic structure of boron is 1s2, 2s2, 2p1. The atomic radius is around 90 ppm. Okay, it's very small size, and also if you look at the valence orbital, the orbitals which are in the valence shell, so 2s and 2p, the 2p is not completely filled. Okay, so it has empty orbitals. So in the trivalent state, boron can be called electron deficient, as it will have only 6 electrons in its outermost orbit. Thus, boron has a tendency to accept lone pair of electrons from other compounds to become a stable molecule, otherwise it will be attacked by other nucleophiles. This property also makes the compound a Lewis acid. Okay, it's a Lewis acid. That means it can accept electron, a pair of electron, not a single electron, it's a pair of electron from other molecules. Okay, so boron is very crystalline solid, okay, and also it's chemically very inert. Okay, even if you take a solid of boron and put it in boiling HF, hydrofluoric acid, or HCl, nothing will happen. It will remain the same solid. Okay, so it has 2 isotopes. One is B11 and B10. I believe Professor Muthuswamy would have mentioned about what is isotope and their paramagnetic ratio, why it's important in NMR. Okay, I don't want to spend time on that. So instead of that, this B10, boron 10 isotope, has a very special property. That means it has a very high neutron cross section. Okay, why it is important? It's very important in the sense it can control, it can absorb the neutrons much faster than the other things. So it can control the nuclear reaction. I believe in your undergraduate level you have studied nuclear chemistry, of course in your master level as well. So the control rods, whatever people are using in the nuclear reactors, are made up of boron carbide enriched with B10 isotope, which can quickly absorb the neutrons and control the reaction. If the reaction undergoes vigorously, then the boiler will be lost. To control those vigorous reactions, one can use these things. And also boron used in various pyrotechnics like various light works. Not only that, this is the only preparation method available for making pure boron. If you come up with a new reaction route to make pure boron in tons and tons of scale, you will be highly wanted in DRDO lab, because DRDO are looking for a pure boron for some other purpose. I will come to that a little later. Let me quickly brief about this basic reaction. It's a borax ore. In the metallurgy you would have studied in your +2. So this borax treated with soda as treatment will end up with sodium borate, and reaction with sulfuric acid produces boric acid. This is what we see, this boric acid in our lake sedimentation. That's why many village people take the lake sediment and apply it on their bodies to make their body more shiny. So boric acid there in all your powders, talcum powders, all the body products. Okay, this boric acid dehydrated under about 170 degrees Celsius will get metaboric acid. Dehydration of this metaboric acid will give you the pyroboric acid. Further heating will end up with boron trioxide. Then reduction with magnesium will end up with metal boron element. Okay, so you need very high temperature to bring this one. If you minimize the temperature and come up with a simple route, you are most welcome to do that. It's one of the major challenge among boron chemists are facing today, and also it's very highly wanted element in our country defense as well. Okay, and also during your +2 you might have done borax bead test. Let me give you the quick recap of that. So if you take the borax and heat it, you'll end up with sodium borate, sodium pyroborate. Then heat it further, you'll end up with sodium metaborate plus boron oxide. In this mixture, we add our metal salt. For example, if you add a cobalt salt, you will get a cobalt borate, which will give a blue color in the flame test. And if you take nickel, you will end up with the brown color flame. If you take copper, and you will end up with dark blue color things. And if you take chromium, you end up with green color. So these are the interesting colors you might have absorbed. It's very useful to find out the metals in a given mixture, not only for your practical things in the wars also. Okay, and another interesting compound, one of the boron compounds is boron carbide. I mentioned it. The rods made up of this one are used as control rods in nuclear reactors. And so this simple, if you look at the molecular formula, is very simple, B4C. But if you look at that structure, it's really complicated, isn't it? If these are the blue networks are borons, it's not a simple. Okay, it's a highly complicated structure. Then the carbon is embedded in this one. Okay, this is a B4 carbon. So it has a lot of application. One can make this compound following this procedure. So you take the boric acid and reduce it with carbon in electric arc. You end up with boron carbide. One of the great applications of these elements is one can make bulletproof jackets, lightweight combat fighters, and also lightweight rifles. Okay, it's very hard element, but also weight is very less. Okay, and I'm moving on to another interesting compound, which is boron hydrides. So you attach 3 hydrogen with boron, it became a borane, but it's not a simple borane. It dimerizes because this is electron deficient, so it will dimerize to form a B2H6. Okay, so Alfred Stock, he was the first one to isolate these boranes, all the boranes, using various chemical reactions, because he prepared a special apparatus where he can isolate sensitive compounds. Before that, nobody had that type of apparatus, so nobody could be able to isolate those kind of compounds. These compounds are very interesting in the sense, if you look at their boiling point, this first one, diborane, it's minus 92, that's why it's a gas at room temperature, and also other one, also it's gas at room temperature, the remaining and all solids. Okay, and one more interesting historic note about Albert Stock is that he's the student of another great scientist, Fisher, and he also worked with, Albert also worked with Henry Moissan. These two are the great scientists. They're well known for their chemical reactions. Okay, the structure of diborane gave a lot of information and intuitiveness to define what is chemical bond. Okay, the chemical bonds are defined based on the dative bonds formed by the Lewis acids and the Lewis bases. So this person, William Lipscomb, he spent a lot of his life in establishing the structure of these molecules, and also he's a very good NMR spectroscopist as well, especially on boron. So if we look at this diborane molecule, the 2 boron centers are bridged between 2 hydrogens. So these terminal hydrogens, we call it 2-center 1 and 2, 2-center 2-electron bond. So this bridged hydrogen, we call it 3-center 1, 2, 3. So 3-center 2-electron bond, only 2 electrons in the 3-center. Initially, everybody thought that if it's bond means only 2-center will share 2 electrons. But here they proposed that more than 2 centers can share 3 electrons. Okay, so for this he was awarded Nobel Prize in 1976. Okay, so another interesting about this boranes is that one can use it as a reducing agent. One can reduce aldehydes or ketones into alcohols, or even esters into alcohols, epoxide ring opening, lactone ring opening, and amide hydrogenation and nitro reductions. One can do this. These reactions were done by another great scientist, H.C. Brown. He is also a Nobel laureate for his work on diboranes reduction. So, okay. So, one more interesting aspect of this borane is that if you look at the boranes, decaborane, diborane is a fuel name, and there how much heat they release. If it's a fuel means, I mean, a compound, if you burn a compound, how much heat it releases. So this JP4 I mentioned here, but it's supposed to be JP10. So that is the jet fuel people are using in rocket launching and other things. Okay, it's a mixture of kerosene plus gasoline and hydrogen. So it's, if you look at its value, it's 18,400. Okay, but if you look at the amount of heat one can produce from burning the boranes, that means boron hydrides, its first one is decaborane, one can get 27,850. For diborane, one can get 31,078. For pentaborane, one can get 29,000. So much higher than the value what one can produce from these things. That's why in the beginning, people thought of, as soon as they discovered this concept, people thought of using these boranes as a fuel for rocket launching and other things. Okay, they did use this as a fuel for rocket. The only problem they faced was when you burn boranes, the byproduct will be the boric acid, right? It's a borate. So it's a highly abrasive compound. It deposits on the engine. So as a result, one cannot reuse that engine back. So we have to dump that engine for after a single use. So because of this, people dropped that ideas in 80s, but now it had a lot of attention because even our DRDO lab, in collaboration with few labs in our IAC, they're trying to use this boron as a fuel for missiles, because missiles, we are not going to reuse that launcher, right? So if it goes and hit, it serves its purpose. So we want to use these boron-based fuels for launching missiles. This, if anybody interested in, please check in DRDO websites. Okay, other one is that the boron main group elements. So this boron can couple with other main group elements like magnesium, sodium, calcium. It form a nice, we call it metal borides. These metal borides have a lot of interesting application. One of this is levitation. That means if you keep these kind of superconducting materials on top of a magnet, they levitate. That means there is no touching. There is a gap between this and this. There is no touching. That means one can reduce the friction and one can enhance its speed. That's what in bullet trains Japanese are used in the beginning. Okay, levitation force. Okay, boron compounds have a lot of application in those kind of areas as well. And another interesting compound is you would have seen in your textbook. It's a boron nitride. The structure is similar to graphite, but it's not exactly the same. Okay, it has, in graphite you have a fully carbon system, but here you have a boron and a nitrogen alternatively. Okay, it's a hexagonal nice structure. This boron nitride presents two forms. One is hexagonal sheet, another one is 3 dimensions like your diamond. Okay, covalent structure. So the crucibles made of this one are useful in melting iron and so many things. And also one can make boron nitride ceramic insulators for high voltage wires. And also these materials, these hexagonal polymer of boron nitrates are highly useful as lubricant. Okay, since these sheets are stacked one another, so when you apply a force, they can move one top of each other. Okay, instead of for heavy duty purpose, one cannot use the liquid lubricants. That's what we use, silicon grease and so many things as a lubricant. But for heavy duties, for tons and tons of heavy duty works, one cannot use a grease because they will evaporate or they can catch fire. But one can use this boron nitrate as a lubricant. One of the interesting application of this boron nitrate. Okay, so for I quickly summarize about the important applications of the boron compounds, whatever you know already. But this area is picking up very quickly nowadays, getting a lot of attention. If you replace 3 hydrogens in the borons center in the boranes with aryl groups, the phenyl groups, one can call it a tri-aryl, 1, 2, 3, tri-aryl borane. Okay, so these compounds find a lot of applications like sensing, because it's a Lewis acid. One can sense anions, and also we can make frustrated Lewis pairs. I will get back to this one a little later. And one can generate solid emissive materials and organic LEDs. I mean, most of you have smartphones nowadays. The screens are made up of these kind of LEDs, and also imaging, tissue imaging or your cancer cell imaging and so many things. So, okay, I will briefly touch upon a few topics where we are interested in. So as I said, in tricoordinated boron, the number of valence orbitals involved in bonding are higher than the number of valence electrons. As a result, it left with one p orbital. This is the empty p orbital, which stands perpendicular to the coordination plane. That means coordination plane is the trigonal planar. This the trigonal planar plane is sp2 hybridized. So since it has a empty p orbital, it's inherently electron deficient. Okay. So if you add any nucleophile, the nucleophile can accommodate in this empty p orbital. That means the lone pair can bind to this one. So this molecule is electron deficient, coordinatively unsaturated, right? So once bind to the nucleophile, you go to the 4 coordinated species, 1, 2, 3, and 4. 4 coordinated. Now its coordination is complete, it coordinatively saturated, and also electron sufficient. So there is a huge differences, electronic as well as structural difference between these 2 units. We exploit these structural and electronic differences to develop various sensors and other things. And also instead of this simple nucleophile, we try to use a nucleophile based in enzymes. So if you bind this boron into the nucleophiles in the active sites of enzyme, one can modulate the activities of enzyme. We call it as a enzyme modulators. Okay. Apart from that, if you take a electron-rich substituent and attach to electron deficient, there will be a there will be dipole. That means the electron can flow from donor to the acceptor. Okay, it can be a good donor-acceptor system. And also, if you attach this boron into a conjugated system, you have a carbon pi system. It's a unsaturated thing, so you have a orbitals which can have a nice interaction with this. That means one can enhance the conjugation much better in these materials. Okay, and also if you look at this carbon-carbon double bond, this is a homodiatomic. That means it's both are same atoms. We call it homodiatomic carbon unit. If you look at this one, boron and nitrogen, it's a heterodiatomic because these 2 atoms are different. But if we count the number of electrons involved in bonding, here it's 8. Here also it's 8. 3 plus 5, 8. 4 plus 4, 8. So it's isoelectronic unit. Okay, it's a double bond, genuine double bond. But if you look at this boron and nitrogen, boron is less electronegative than nitrogen. As a result, the sigma bond electron mostly reside close to the nitrogen. But nitrogen has a lone pair. This lone pair attracted towards the empty p orbital on boron. So as a result, there is a synergism in the bonding. There is a synergism like your metal carbonyl. Carbonyl donates the electron, and metal donates back the electron to the carbonyl to the empty p orbital. Likewise, here you have a nice synergism. We exploit this synergism for making materials and other things. Okay, this I will skip this part. So most of my lecture will be about the luminescence. So I just want to brief what is luminescence for the undergraduate students, especially. If you take any molecule or a material, we call there may be a ground state. We call it S0, that is the ground state, and you will have a excited state. Like in your NMR, you have a ground state and the excited state, alpha and beta spins. Okay. So here, once you give energy, that energy can be a temperature or potential, like electroluminescence, or a photons, like a light. If you give a photon, it can go to any energy level, S2, S3, S4, or else. After going to a higher excited state, it will come back to its lowest excited state. From that process is called internal conversion. Okay, internal conversion, coming from higher energy state to the lower energy state. Once it comes to the lowest energy state, from there it can emit light. It would always emit light from the lowest excited state. That is called Kasha's rule. So if the light comes from this one, then we call it fluorescence. Okay. All the molecules will have a triplet as well, triplet state, excited states. But the triplet levels always lower in energy than your singlet state. Okay. So as a result, if it goes to the excited state, it can also go to this triplet state as well. This process is called inter-system crossing, because the spin here it's a singlet, here it's a triplet spin. Okay, triplet is both the ground and excited state will have the same spin. Here in a singlet you will have a opposite spin, up and down. Okay, so as a result, going to the singlet spin to the triplet spin, we call it inter-system crossing. Once it goes here, it may radiate from a triplet to the singlet, then we call it a phosphorescence, or it can come back to the singlet state. As like forward, it can come back to the singlet state. If it comes back to the singlet state, we call it reverse, because it's coming back, a reverse inter-system crossing. Okay. If it comes back to the singlet state, then again it can emit from the singlet. And it's called fluorescent, but at this time, this is spending some time in this triplet. As a result, it's getting delayed. Okay. We call it a delayed fluorescence. Okay. These are the basic concepts one should know if you want to understand what is luminescence, what is phosphorescence, what is fluorescence. Okay, when you don't know what is phosphorescence or fluorescence of your compound, we'll call it a luminescence. It's a luminescent materials. Okay, if you know it comes from singlet, we say it's fluorescence. If you know it comes from triplet, we call it phosphorescence. Okay, I hope it's clear to you. So since this tri-coordinated boron has an empty vacant site, so we use it as a sensor. I will give one simple example how we exploited this very simple concept. So this periphery, this is a porphyrin ring with 4 pyrrole units connected through a use of carbon, and the periphery we have a boron unit. Okay, this center are boron units. Okay, in the center of the porphyrin we have another metal which is zinc. Okay, so all the time I believe all of you agree with me. This zinc can also be a Lewis acid. Okay, we have 2 Lewis acid. One is at the periphery, boron-based Lewis acid, and center we have another Lewis acid, which is zinc. Okay, so the boron is a hard Lewis acid, so it prefers to interact with a hard base. Okay, fluoride. Okay, it's a hard base, but it's a weak base. So it prefers to bind to boron, hard interactions, and stop the energy from here to here and quenches the fluorescence. But the cyanide, it's a carbon-based nucleophile. That means it's soft nucleophile, which can bind to the zinc center. Okay, so it's not going to the hard boron. So it touches only the cyanide. As a result, it modifies the symmetry of the porphyrin and changes its absorption. So we can detect both the ions using a single molecule in 2 different channels. One is fluorescence, another one is for absorbance. Then we generalized this concept and went ahead with, instead of having these test tubes, can we have a strip? So we developed a simple strip-based sensor for these anions, which is much more sensitive than the commercially available cyanide sensors, which is 20 micromolars, ours is around 1 ppm level sensitivity. So as I mentioned earlier, we can also develop a lot of solid, colorful materials, find application various field by just modifying the interaction between this boron center and the incoming pi system. It's just I kept a benzene here. The benzene, it has a p orbital which stands perpendicular to the benzene plane, right? The pi orbitals. Okay, that's what here. So these pi orbitals can have an interaction with this boron center, empty p orbital. This interaction one can modify it by twisting their dihedral angle. If they are in same plane, the interaction is stronger, conjugation length is longer. We twist them, the interaction is going to be reduced. The conjugation length will be reduced. As a result, absorption and emission will be different colors. So just by exploiting this very simple concept, we developed a lot of solid state emissive materials. One can, of course, you can also do it very simple reactions. Okay, just this is all for data. But what we do with these multiple emissive materials, one application is that we can scan or image your tissues, the tumor cells or any diseased tissues in different colors. Why it is important? It's important because the tissues, our tissue itself have a lot of luminescence. If you want to image it properly, how the morphology is changed from undiseased cell to the diseased state, one should have a proper morphology. One should understand the proper morphology. Or that if the tissue itself luminescence means there will be interference. You cannot image it properly because your normal cell itself has a lot of luminescence. So especially green color. To avoid that one, if your compound emits in different colors, one can switch the colors and image them. We developed a simple molecule which can give a single molecule, small molecule, which can emit white light. That means 3 colors. So we can image the cells. These are all your tumor cells, and we can image them in red, blue, and green. Okay, this is the composition in this white. One other application I just want to show where we use these molecules for other purposes. And also we developed another molecule. Instead of 3 colors, we can almost 5 colors: NIR, red, yellow, green, blue, cyan blue, and blue. These are merged things. So now we have a single molecule which can emit lights into complete electromagnetic spectrum from your blue color to the NIR region. Complete visible. Apart from visible, we can also go to the NIR region. Okay. So these are the few applications we apply our boron compounds. So another interesting topic I would like to mention, touch upon, is that external stimuli responsive materials. Okay, what is external stimuli? The stimuli may be your pressure or temperature or some other things. Here I kept 3 examples. What is the use of these materials? If the luminescence of your materials is sensitive to pressure or temperature or light, we call that external stimuli responsive materials. Here, one of the advanced application is the fingerprint analysis. Apart from the current fingerprint analysis, people are moving forward to the stress-dependent fingerprint analysis, and also secret writing. One is something called secret writing, because we are normal people, we don't have anything. But people in a higher position, like prime ministers or somebody want to send us some note. Nowadays, everything is open to everyone because of the electronic medium. So something called the secret ink. It's made up of these oligomers. Some text is written on this white color paper. If you see it in a visible light, we don't see that text in that one. It's a simple white paper. But if you shine light, that means a UV light, this oligomer undergoes photoreaction. That means cycloaddition reaction, right? 2+2 cycloaddition. It forms a oligomer. When it forms a oligomer, the conjugation length enhances. As a result, it appears, the colors. This is UV. It's not visible. Once it becomes polymer, it's visible. Also, if you see, the adjacent molecules have a nice hydrogen bonding between the acid units. As a result, there is some strain in this molecule. As a result, it's blue color. Once you heat it, then this hydrogen bonding breaks down. Then the molecule has a lot of freedom to adapt a more planar conjugated state. Then you can see the color shift. higher wavelength region. And also people have developed materials, polymeric materials. Using those materials, one can measure the stress, how much stress is applied when two daughter cells comes from a single parent cell. Okay, it's a cell division. It occurs in our body every day, right? So how much pressure is applied during that cell division, one can measure using these kind of. That's why these kind of materials are highly useful in various applications. Okay, here the stimuli is stress. Here the stimuli is light. Here the stimuli is a pressure. Okay, whenever you touch something, you're applying some pressure. That pressure will be recorded using these compounds. Okay, so we exploit this simple boron chemist to develop this external stimuli responsive material. For example, I have shown here is a boron, 3 aryl groups attached to that one. This molecule is propeller in shape, like this propeller. Each one, if you consider this wings as a fans as a phenyl group, it's a propeller shape. Okay. Here we are connecting our electrical things, right? Electrical wire to spin this fan. Here we have a boron center where we can attach some other stuffs. Okay. So if you introduce a donor electron, for example, here I am showing amine. It has a lone pair on this nitrogen. So this lone pair can be shared with this electron deficient boron center through this double bond of this benzene. Okay. This sharing, that means this lone pair goes to the boron center. This sharing can be controlled again depending upon the orientation of this phenyl ring. This phenyl ring, how it's oriented towards its boron center. If it's perpendicular, the charge flow will be less. If it is in plane, the charge flow will be more. So depending upon the pressure, how much pressure we are applying, then one can modulate this rotor. We call it this a rotor. This rotor, depending upon this rotor angle, the charge flow from here to here will vary. So using this one, we came up with some materials which we can measure the pressure as low as 0.02 GPa. Okay, so this is not very interesting one, but I want to show something which is much more interesting than that. So when you say viscosity, I mean all of you aware of viscosity. Okay, viscosity and the temperatures are inversely proportional to each other. Okay, we developed some molecules because, as I mentioned earlier, here, depending upon the viscous of the medium, the free rotor can change its conformation. If it's dilute, it can rotate faster. If it is viscous, it can rotate slower. If it's really viscous, then it can restrict. So, just using this very simple concept, we developed a rotor which is sensitive to the luminescence, is sensitive to their viscosity. Okay, two components. This here it is. When you increase the viscosity, the luminescence is enhances. Okay, here also the similar. Okay, this is the intensity and its viscosity. Okay, the relative intensity and the sample viscosity. Okay, if you increase the viscosity, the luminescence is enhances very high. Okay, that's what. So where we can apply this? These are the two molecules. Again, we have a boron and a donor phosphorus here. So instead of nitrogen, we are having phosphorus here. Okay. So why these viscosity-based probes are important? I will let you know here. So the tissues in the cells, I'm talking about the cells in our body. There's a different viscosities of different states. Okay. The cancer, Professor Vivekananda is sitting there, and he may know more than me about these type of cells. So the cell, we call it a HeLa cancer cell. It has a low viscosity, but before it dies, it will undergo two different pathways. One is apoptotic and autophagic pathway. Either way, in both the pathways, the cell shrinks. As a result, the density inside the cell is much higher. Okay, before it died, the density became higher. So he measured those densities using AFM technique, atomic force microscopic technique. So these are the tissues and their viscosity in this scale. Okay, so we apply pressure on the cells and see how it behaves depending upon how much pressure we are applying through this cantilever of this atomic force microscopy. Then we plotted it. Here you can see this before it undergo death, commit suicides. It has a different very high density. So can we use our probes to probe different stages of these cancer cells? Okay. So we use these molecules, and this is called MTT assay studies. That means whether your compound is acceptable to the cells or not, whether it enters and keep the cells alive or happy or not. So our compounds enter the cell and also keeping the cells alive. They are not killing the cells. That means the probe should not kill the cells, but your drug molecule should kill the cells. That's the difference between a probe and a medicine. Medicine should kill the cell, but the probe, if you want to probe it, it should not kill the cell. Okay, that's what it's keeping the cells happy. That means it's non-toxic. And we used, again, these are the cells under microscope, fluorescent microscope, after incubating with our compound. This is a HeLa cell. This is autophagic cell. I said the disease state, and also apoptotic state. In all these states, if you look at this thing, our compound emits differently. Here in autophagic, it shows a different color, different intensity. In apoptotic, in autophagic cells, it shows different intensity, and HeLa cells shows different intensity. In autophagy, as I mentioned, in autophagy and apoptotic, the density is more, viscosity is more. As a result, it's strongly luminescent compared to the HeLa cells. Now we established our concept that yes, we can detect the viscosity in these tissues using our compounds. But what else we can do with this? So once we establish the concept, we have to demonstrate it with the disease model. Okay, so we took Alzheimer's disease as a model. What happens in the Alzheimer's? Your brain cells are getting died slowly. As a result, you are losing your memory. Okay, that's means your neuronal cells getting damaged during the Alzheimer's disease things. So, but the basic concept is cells, the fresh cells, before going to death, it will go either autophagy and apoptotic state. Okay, so that means it will undergo condensation. So far, there is no probe to detect the early Alzheimer's disease. Okay, so that's why people are interested in developing this kind of. What did we do was we take the mouse, okay, ball mouse. Just after their birth, we cut open their brain and take those neuronal cells. Okay, just one word. No. So these are the neuronal cells. I hope it's visible to you. Here you can see the raw shapes. These are neuronal cells. Then we grow them, and these are the neuronal cells without our compound. Okay, and these are the fresh neuronal cells. These neuronal cells were induced. We induced apoptotic. We gave some compound, make the cells die. Okay, we induced two things. One is autophagic, and another one is apoptotic. Okay, if you see the normal cells, our compounds is not showing any luminescence. But if you look at the autophagic and apoptotic cells, our compounds are lighting up them. That means, yes, we have a probe which can detect early stages of Alzheimer's. Okay, of course, there is a long way to go about this one. We are under further studies with our collaborators in the Biological Brain Research Center. Okay, let me switch the gear a little bit here. I spoke about sensor, okay, and also solid emitters. With one or two examples, I didn't really explain what it is. And also, I don't want to touch up on this one. I also mentioned something about imaging, how it's useful in scanning different diseases. Okay, so now let me move on to another interesting topic, which is called the frustrated Lewis pairs. So I hope all of you still alive now, because last 2 days lectures you may be frustrated quite a lot. I also don't want to frustrate you further, but this title is very interesting because I kept this title especially not to frustrate you, make you happy. Okay, you'll enjoy this part. What is frustration? Okay, everybody has frustration in their life, right? If women get frustrated, what do? They can pull their hair because they have a lot of hairs, but I have very less. But Professor Muthuswamy has very lesser than me. And if the guys get frustrated, they have some other thing to do, but I advise not to do these things. But sometimes what happens if an animal gets frustrated? Okay, if an animal gets frustrated, they do. Sometimes they even shout at us. Okay. Sometimes these kids make their mom getting frustrated very much, because sometimes they have to really beg to their kids to behave properly, but they don't listen, because see, look at him, he's shouting at his mother. But guys, we have a different way of dealing these things. What we do, we shout at them and control them. Okay, so in all the three cases, what we do, we behave differently to the frustration. That's what I mean. Okay, so when the lovers get frustrated in the beginning, they behave very polite. They turn aside as if like they don't want to speak to each other. Okay, but once they get married, they will show their frustration a little different. Okay, they shout, or if you get married after you giving birth to one child, you'll get beaten up, right? The frustration goes. Also, as a teachers, we do get frustrated when you don't look at the screen and do something else. Instead of listening to the lecture, if you do something else, obviously teachers will get frustrated. Okay, so the frustration is everywhere. Sometimes it's very useful in the sense one can get rid of the things, unwanted things, can break and throw it, right? Because we have a lot of energy. But sometimes if you channel those frustrations, one can do good things, isn't it? So now you know what is frustration. I want to tell you what a frustrated molecule can do for you. Okay, that's why I kept it frustrated fluid spares. It's a molecule. So, but this title has two different things. One is, I told you what is frustration already. And Lewis pair, pair means two, right? Two things. Lewis pair. Lewis means Lewis acid and Lewis base. Okay, you have a Lewis acid and a Lewis base pair. That is called, that's why I call it Lewis pair. Okay. Here it's very simple example. It's acid with the electron acceptor EA. Electron acceptor, that is Lewis acid. Electron donor, it's a Lewis base. When you mix them together, one can form a Lewis acid base adduct. This is the first example of Lewis acid base adduct, which helped a lot to define what is chemical bonding 100 years before. Okay, but if this electron acceptor and the electron donor, that means Lewis base and the Lewis acids are a little bigger instead of smaller, little bigger, they cannot come and form dative bond. That means they want to interact because he has an electron, he wants that electron, they want to take that, but they cannot interact because of this steric crowding. That means there is a molecular frustration between these two units. Okay, this unit want to give, this unit want to take, but they cannot share the electron because of the crowding. So as a result, there is a frustration and also electric field between these two molecules, a lot of field between these two molecules. So it's a frustrated, now it is called a frustrated Lewis pair. Okay, so this is a real example. For example, if you take a diethyl ether and interact BF3, it's a Lewis acid, it forms a nice dative bond. But if you take tertiary butyl group, tertiary butyl phosphine with triaryl boron, it cannot form a dative bond. This pair is frustrated pair, but it's a nice Lewis acid base effect. This. So what we can do with this frustrated pairs? So interestingly, in 2006, this scientist, Stephen Douglas from Canada, he introduced, if you look at this one, this Lewis acid, boron with the electron deficient aryl groups. Okay, he added another Lewis base. So it formed a product where you have a phosphine and the boron, the electron rich and the electron deficient system. These two systems very nicely cut the hydrogen, one of the strong bond, So it's not that easy to cleave the hydrogens. You need metal. That's why for hydrogenation reactions, people use a lot of transition metals to activate hydrogen. So by here, we don't use any metals. Simple, it's a non-metals. One can activate the hydrogen. So this is the scientist performed this one. So one can utilize this frustrated Lewis pair to activate small molecule. This I just showed hydrogen, but one can use for other small molecules as well. The first hydrogen activation was done by Sabatier sometime in 1910 using nickel as a catalyst. Okay, so this here he activated hydrogen and reduced carbon dioxide to methane. It's a very nice reaction. He performed it in 1910. Now it's almost 110 years. Not okay. Once he demonstrated this reaction, everybody thought that only we can use metals to activate hydrogen. How metals activate hydrogen? This is how it activates. You have a filled electron as well as an unfilled electron, orbitals in the metal. So this hydrogen sigma filled orbital donates the electron to the empty orbital on the metal. The filled orbitals on the metal donates the electron to the antibonding orbital of hydrogen. That means once you put electron density on the antibonding orbital, you are reducing the bond order, right? What is the bond order? You have to subtract the electron from the bonding orbitals and the antibonding orbital and divide by 2, you get the bond order, isn't it? So here, when you start pumping the electron to the antibonding orbital, you are reducing the bond order. One can easily cleave the hydrogen. That's what happening in the transition metal based hydrogen activation. But what happens if you want to activate? That means you have to have a filled orbital as well as the empty orbital. But here in frustrated Lewis pair, we have a filled orbital from the phosphorus, the donor, Lewis base, and you have an empty orbital from the boron. Instead of single metal, we are using two simple atoms, main group atoms. So these two atoms combine together do the job. They cleave the hydrogen here. This is how hydrogen get activated in frustrated Lewis pairs. This is how hydrogen is activated in transition metals. Okay. So using these frustrated Lewis pairs, one can activate not only hydrogen, one can do many things. Carbon dioxide one can activate, carbon monoxide one can activate, and nitric oxide activation, N2, C, like SO2 one can also activate, CO2 one can also activate SO2. So many things can be done with a very simple main group elements, frustrated Lewis pairs. Okay, so how much time do I have? Mail Murugan?
Sir, it can take 5 more minutes because one more speaker has also there. It's nice if you wind up as early as possible. Thank you.
I lost 15 minutes, 20 minutes,
Yes,
20 minutes.
Yes,
So just I want to back up a little bit. I don't want to spend much time because I want to give the time for the next speaker as well.
Yes, thank you.
So I'll briefly mention about what are the other things the boron-based materials are useful in, and boron in medicine. So these are the sources, natural sources for boron. Okay, so you get avocados and a lot of nuts has a lot of boron sources, natural sources. But till now, nobody knows what is the exact role of boron in human body. But chemists are well established for plants. Plants need boron for their growth. For human, nobody knows what, but they said it's essential for human being. These are the natural sources for boron. Okay. Also very interesting. These are the two natural products containing boron. Okay, these two natural. After discovering these two natural products, these molecules revolutionized the boron medicinal chemistry. Only two natural products are known with this one. This one is a boromycin. It's a natural product, and also this one is called. After inducer, this molecule is involved in bacterial quorum. Okay, if this molecule is there, this bacteria, one bacteria release this molecule means all the other bacteria comes and attack that place. Okay, it's called the, that's why it's called the at inducer. It will invite all the other bacteria to make the infection very fast. Okay, quorum signaling. That's why it's called a signaling. This is one of the signaling molecule in bacteria. Okay. So the very simple chemical, as I mentioned in the beginning, it's one of the ore. The boric acid. It's present in our lake sediments, but it is a lot of interesting applications. Like we use it as cleaning materials, hand soap, toilet bowl cleaner, laundry agents, and so many things. And also it's also a plant for rice field or any whatever the cultivation we do. We spray this, right? We go down, and also we put some borates as well in the solid form. And also a lot of creams are made up of these boron based materials. Okay, some of the creams what we are using for your various things, it contains boric acid for its disinfectant properties. These are the boroplast and these things. And another interesting application of boron is that, as I said earlier, the B11, the B10 has a very high neutron cross section, so that it can absorb neutrons. So it's useful in BNCT. It's boron neutron catcher therapy. It's the only therapy available for brain tumor curing. And one more boron based drug is that bortezomib. You can see the instead of, it's a peptide, right? You have an acid and amine, you form a amide bond. It's a peptide bond, we call it peptide bond. So in regular peptides, we'll have a carboxylic acid, COOH, CO, right? So here we have a BOH twice, it's boronic acid. This is a very good medicine for multiple myeloma cancer treatment. It's many of our Indian hospitals are using this one. And another one is a boric acid based. There is eye drops and killers for cockroach and many things are there. Okay, and these are the molecules, boron based molecules. If you remove boron and put other things, it's called dopa, but if you put boron, it's a different name. Okay, this tryptophan based, phenylalanine based drug. And so this, I will skip this one. As I mentioned about this, another interesting drug molecule, boron-based drug molecule is this is recently available for fungal treatments. One is a very interesting molecule because both these two molecules, though the companies are from abroad, these two molecules are developed next to IISc, somewhere in Yeshwanthpur, in the biolabs. So many of MKU students are working there in that particular lab. So these two drug molecules are developed in the biolab, which is very close to us. Okay, and this I already mentioned, Valcard. And so what we do in this part of research, we also do some medicinal aspects of boron. So I mentioned that this boronic acid acts as a drug in multiple myeloma. So we combine this boronic acid because these drug molecules are not stable in bloodstream. So to make it stable, we combine this one with this catechol because the catechol form a nice chelate with the boron, this boronic acid. So we make it dendrimeric molecules with the pendant catechol and tag these drugs so that we have a dendritic molecules with the drug molecules. So we use them as a pro-drug. So yes, these dendritic molecules are more stable, okay, and once they enter the tissue, because of the pH gradient, it can open up and release the drug molecules. Okay, that's why you can have both catechol. Catechol is also a redox-based drug. So we have two drugs from one pro-drug kind of dendritic molecule. That's what we do. I very briefly mention about this. And with this, let me conclude my talk. I believe I give you various examples that how one can exploit the inherent property of the boron. That means the electron deficiency and its coordination and saturation for developing materials and medicinal molecules. With this, let me thank my current students who prepared some of the slides and my postdocs and the funding agencies like Indian Institute of Science, SCRB, CSIR, and Joint Research Center, Solar Energy Research Center for India and USA, and ISRO for their generous funding. Of course, for CRSI for this creating this awareness for among the students. Once again, I thank the organizers for this wonderful opportunity. Thank you all. If you have any question, I will be more than happy to answer mine.
Thank you, Trichy sir, for your wonderful lecture on boron chemistry in various applications, especially external stimuli responsive luminescence materials, boron neutron capture therapy for treating brain tumors, and thanking you for spreading the importance of boron chemistry among the young minds. Now I request the audience participant to raise some questions or clarifications if any. Already I have one question.
Yes, please.
Why triplet state is stable than singlet state in the excited state, the luminescence diagram?
Yeah, it's not the luminescent diagram. If you compare the electronic states of any molecule, when you have two electrons, okay, in the different orbitals, if you have an opposite spin, the spinning, it's more probability that they can come and meet each other. If they are parallel, in the case of triplet, they don't meet each other, right? As a result, the repulsion energy is lower. When the repulsion energy is lower, then the electronic state is lower in energy. But in the case of singlet, they meet each other quite often. As a result, the repulsion energy is high. And also the exchange energy is 2 times higher for triplet, and for in the case of singlet, it's lower. That's why.
But this is contradictory to the Hund's rule, sir.
Lower in it. Triplet states are lower in energy compared to the singlet state. Yeah.
But this is contradictory to the Hund's rule, right? But because when you're filling the electrons, according to Hund's rule, you put the spin will opposite to each other, right? If you put the orbitals, right?
We cannot. Even in the Hund's rule, what they say is, if you fill the electrons, you take an isolated atom, fill the electrons in, for example, d orbital, phi orbital, or p orbital. You have 2 electrons, right? So how do you put it? Will you put the 2 electrons in the same orbital in opposite spin, or 2 electrons in the same spin in 2 different orbitals?
But they're different orbitals. So when you fill the electrons,
will you put in the opposite spin or same spin?
Same spin.
Why? That's a triplet, right? Configuration. One of the microstate. If you take the P2 electronic configuration and write down the this is called the microstates, right? If you put both electron opposite spin, that is one microstate. If you put the opposite side, that's one microstate. If you put both the electrons in the same orbital, that's one of the. If you compare the energy of those microstates, the orbital with the triplet configuration will have the lowest energy.
Because for helium, we will put the 2 electrons in the opposite spin, right? For helium, fill the electrons. We are putting in the opposite spin, not the same spin.
You can put it then again, as I said, the repulsion energy will be high. The energy of that particular microstate will be higher than the microstate having the configuration having 2 electrons in the same spin.
Okay, thank you, sir. If there is no more questions, I thank Dr. Tilakar on behalf of CRSI and Department of Chemistry, Vivekananda College. Thank you so much, sir, for your wonderful lecture. Thank you, sir.
Thank you.
Professor Meet, Professor Ramesh speaking. Hello, Professor Tilakar.
Yeah, I'm very much there. Yeah.
Sorry, I was not able to join at the beginning due to my personal assignment. And in the middle only I joined. So on behalf of the Trichy-Madurai local chapter, I welcome you. And your lecture is wonderful, which will be most useful to the student. And thank you once again.
Thank you.
Thank you, sir.
Thank you.
So we have just heard of Professor P. Tilakar lecture and hope we are all excited by his wavelength. So we are at the last E-session 3 by Professor J. Sankar, Department of Chemistry, ISR Bhopal. For this session, I request my colleague Dr. G. Rajkumar, Assistant Professor of Chemistry, to chair this session. Welcome, Raj.
Thank you, Eli. Am I audible, Eli?
Yes. Yes, yes,
Yeah,
sir. Yes,
okay.
sir. Please.
So I'm indeed very happy to introduce today's resource person, Dr. J. Sankar sir. So he's a proud alumnus of our college. He got his BSc degree, BSc Chemistry from Vivekananda College in the year 1998. Then he got his PG degree from Mijra College, Madurai. He did PhD in IIT Kanpur under the able guidance of Professor T.K. Chandrasekhar sir, and he is the awardee of a JSPS fellowship in Kyoto University, Kyoto, Japan in the year 2008, and he is now he is a professor in ISF Bhopal. And regarding his administration experience, he is having a rich experience in the administration. He is a dean of faculty affairs ISF Bhopal from October 2019, and he was the dean research and development ISF Bhopal and dean of faculty affairs, and he is the convener of Indian JSPS Alumni Association Western chapter, and he is the coordinator of academic affairs and the convener, and he is holding various positions. And regarding his research, his areas of research is pi conjugated materials for modern applications in inorganic and bioinorganic model systems, and his research interest is in establishing efficient routes to harvest energy from solar radiation using pi conjugated molecules as antenna complexes. And more than 10 students have been awarded under his able guidance, and he has published more than 50 international publications with very good citations in the reputed journals. And with this short introduction, I invite Dr. J. Sankar sir to start his invited lecture. Thank you. Welcome you, sir.
Thank you. Are you able to hear me?
Yes, sir. Yes, sir. You are audible, sir.
Okay, yeah. Thank you, CRSI, for giving me this opportunity. I thank Professor Mail Murugan and Professor Ramesh for choosing our research. And I would like to also thank Vivekananda College and the Department of Chemistry. It's after a silver jubilee time I'm talking in the department. I joined in 1995. It's exactly 25 years now. So this is kind of a very landmark for me to give a first talk in the department of the research what I have done. So before me, Professor Muthuswamy and Professor Tilagar, they were talking about it, and they have clarified most of the basics, whatever I wanted that the students should know. So I will build up from there. On a lighter note, and I just wanted to talk, I just wanted to mention Professor Tilagar. He was talking about frustrated Lewis pair, and then he was talking about the linkage with the hair. So I have much less hair than Tilagar. I don't know where will I hold my hair when I get frustrated. Yeah, now I hope I don't make the students frustrated with the research. Let me go a little slow. And if at all, anywhere, if I go fast, you can slow me down. Okay, so the topic what I have chosen here is porphyrin rylene diamide conjugates for artificial light harvesting applications. So some of the words are technical jargons. I will explain you why this word is coming. And keeping in mind the master's students, when we were doing BSc, there was no master's department, but now you have a master's department. So I have kept the research a little bit less, difficult. And then I will explain you. If at all anywhere you have problems, you can write and then I will explain you. Okay. The first one, I'll explain word by word of my title. So what are porphyrins? All of us know what is blood. And if you ask any undergraduate student who's doing chemistry, why blood is red in color? So they say that hemoglobin. And if you go a little further and then you ask why hemoglobin is red, they say that it's because of the red iron present inside. But actually the color of hemoglobin comes from the heme group which is present inside. And then I have given you the structure of this one here. So this is what we are calling as heme, and this heme is the one which is shown as a disc shape here in the hemoglobin structure. This is the structure of hemoglobin. It has 4 such pockets, and all the 4 pockets have this heme, and which is having iron at the center. So the color of this hemoglobin comes from this particular ligand. This is what we are calling as a heme. And the same heme, you just look at here, I have given a naked structure of this heme without any substitutions. So this is what we are calling as a porphyrin ring. This has 4 pyrrole units. You can see 1, 2, and 3, 4. all the 4 pyrrole rings are symmetrically connected by using a methane bridge. That is nothing but a carbon bridge. So this is the ligand which is responsible for all the biological properties of either hemoglobin, myoglobin, or going for chlorophyll and so on. In all the cases, the difference would be only the substitutions which is on this heme group. Otherwise, this ligand is more or less the same. Second thing, these molecules are supposed to be aromatic because you have 18 pi electrons. As per Huckel's rule, you have 4 and plus 2 electrons, and then if you supply n is going to be 4, you'll be having 18 pi. So this is what, if you count the number of double bonds, whatever I have highlighted, you'll be having 9 double bonds. So 18 pi electrons, so this molecule is aromatic. So what are its properties? As I mentioned, first they are aromatic and they have 2 NH protons inside. So this is the NH proton which has been replaced by a metal here. So it can stabilize metals in various oxidation states, not only in 2+, but it can be stabilizing in many oxidation states. It has a very large absorption coefficient. What I mean by absorption coefficient is, if you say, for example, some food colors, you add a little bit in water, the color used to be a little dilute. But there are some colors, especially the students whomsoever they are aware of this holy festival which is celebrated in North, they might be knowing it. There are some colors, if you use it, even though you are using a very little amount of color, the intensity of the color is going to be very strong. So this is what we, in this case, as a layman's language, I am saying that the molar extinction coefficient. This molar extinction coefficient is a very important factor when it is coming to dyes and pigments. Okay, and these molecules are also having very strong, a very large absorption coefficient. I will explain you what it is and how this can be applicable for our applications. These molecules are not new. There are a lot of synthetic porphyrins available. It's quite more than 100 years people are working in this area. And these molecules have been used for various redox catalysis, light harvesting units in solar cells. And this is what I will be talking to you about this one shortly. These molecules, as Professor Tilagar was talking about, these molecules also have been used for bioimaging, cancer therapy, and for chemosensors. But today I will be talking only about solar cells, so that I will be confining it to only one area. So this is about the one class of molecule what I talked about. One is porphyrin. Second one is rylene diamides. So rylene is nothing but just polyaromatic hydrocarbons. For example, in the case it's naphthalene and you have perilene. So what we are talking about is when you increase the number of naphthalenes in a ring, just keep on increasing, you will be having more and more longer rylenes. That is what we are talking about. The common name is rylene. But you can say naphthalene, then you go for perilene, then pterilene and quaterline and so on. So here I have given you this N. This N is nothing but it's polymeric. You can just keep putting one unit after the other, so the molecule becomes longer and longer. And diimide in the sense, here if you see that this is simply naphthalene, and then I have 2 imide groups connected here, and this is what is making this molecule as rylene diimide. In this case, this is naphthalene diimide. So if I go for the longer alternative, longer analog, then what we have is a perilene diimide, where in which you have one more naphthalene which is connected on the peri positions. So that is what we are calling as a naphthalene. So this, as I mentioned, depending on the number of naphthalene rings, we can have different numbers. So if the N is going to be 1, what we have is sterilene. That means you have 3 naphthalene rings connected to each other, stacked kind of. When you go for 4, then we have N is equal to 2, then you will be 4, then it's called quaterline. And when you have in all the cases, if you have diimides, then you can call us a pterilene diimide or quaterline diimide and so on. So what is so important about these molecules? These molecules are not having any biological roles as of nature. In nature, it is not available, but why should we talk about these molecules? So if the students know about the color of Ferrari car, mostly it is very popular because of its bright orange red color. So that color comes because of this particular unit, which is there used in that paint. Okay, so it is industrially very attractive dye, and this molecule has been used for various applications. Which are the applications which are coming into picture is, one is high stability. These molecules are really very stable and robust. They don't decompose that easily. And strong electron withdrawing, or electron accepting ability. Why this electron accepting ability is coming is you have 4 oxygens connected to this molecule. So they pull this electron density away from this pterilene unit and makes this molecule electron deficient. So when we are talking about some molecules which need to have electron deficient or some molecules should have electron rich nature, then these kind of substitutions become handy. That is why this molecule is very important. And as I mentioned, they are well-known industrial colorants. they have high electron mobility and make them suitable for organic electronics. So this word, I thought about it and after that only added, but remember that when you have high electron mobility, earlier we were discussing about some organic molecules which can be made conductive. Usually organic molecules don't conduct. So how do you make them conductive is nothing but you have to make this molecule have the ability to transport the charge what is on it, whether it is going to be positive charge or it is going to be negative charge. If that can be used to conduct the charges, conduct the current, then what you can say is that their electron mobility is going to be more. So these molecules have very high mobility. Because of that, these molecules are applicable in organic electronics. Organic electronics in the sense, the screen of your mobile, for example, OLED screens, whatever we have, those are all the molecules. Some of them are related, structurally related to these molecules. And these molecules have been used as building blocks for many supramolecular assemblies. Supramolecular assembly in the sense, if you want to prepare a molecule which is as large as possible, you don't need to have covalent bond between small units and then make a big molecule, but rather you can go for some pi stacking or some secondary bonding. Using that, you can make a big molecule. So this kind of chemistry is called supramolecular chemistry. So these molecules, all this class of molecules have been used as building blocks for this one. So I have given what is the photophysical advantage of this molecule. Now, if I take this as I have given intentionally pteryline diamide. In the case of pteryline diamide, that is only 2 naphthalene rings are there here. You see the absorption maxima, this is around 530 nanometer, and then you see the molar extinction coefficient, which is around 50,000. Okay, so it is not very strongly colored, but the fluorescence is very good. When you go for larger and longer molecule, what is happening is I have given the next one, which is TDI. When you have more than 3 are going to be there, so then the absorption has gone redshifted. And when the absorption is getting redshifted, the epsilon value is also increasing. That is molar extinction coefficient. It has gone double. Okay. So the absorption redshifting that you might be knowing, when you talk about any pi conjugated system, if you increase the conjugation, what you are doing is you are reducing the gap between a HOMO and LUMO. When the distance between, energy difference between the HOMO and LUMO comes lower and lower, then the wavelength of absorption of this molecule goes towards the red side. Red side is towards longer wavelength. So this is what we call as a bathychromic shift. So this is what is happening when I increase this molecule longer wise and lengthwise, and then the absorption shifts towards the right side. And when I go longer and longer, this molecule has fantastic absorption profiles. For example, when I have 6 naphthalene rings connected this way, that's like a long rope. And in that case, the molecule has a molar extinction value of, say, for example, 3 lakh. That's a huge value. Okay, usually, most of the organic compounds don't have this kind of values. But this application doesn't come without any problems. So this has some problems. The problem is, when you talk about this kind of larger and larger pi surface molecules, these molecules will become more and more insoluble. See, for example, if I want to dissolve naphthalene, I can easily dissolve. Pteryline is comparatively okay. Then when I go for a little longer, like quaterline and pentarylene, then what happens is these molecules try to stack. So that is what I wanted to show you here. So in this case of, So I'm sorry, this scheme has changed. Now you see this benzene ring, for example. When you stack 2 benzene rings like this, so these molecules stack with each other. As a result of this, what is happening? This stacking doesn't stop with only 2 molecules. So you'll be having more number of molecules above this. As a result of this, this forms an aggregate. Once this molecule becomes aggregate, it doesn't dissolve. So this is what one of the problems with respect to these molecules. And in this case, this kind of pi stacking, when it happens is, whenever you have a molecule which has a larger pi surface in the sense what I mean is, it has a pi conjugation. At the same time, the molecule is supposed to be planar because they are aromatic. And then when they become larger and larger, then the stacking becomes more and more feasible. As a result of this, they become insoluble. That's why I was telling you earlier that when I increase this length of this PBI longer and longer, then the solubility gets suppressed. Okay, so this suppression, it not only happens with the PBI, it also happens with this case of porphyrins. So that is why I was mentioning about this stacking earlier. Now, if I want to now use these molecules for applications, what I need to do is I have to first make this molecule soluble. At the same time, it should be useful for me for other applications. Before getting into the main selling point of this molecule, I just wanted to give you a brief overview about what are their properties. In the case of perilene bicimide, just only 2 naphthalenes are connected to each other. This is called perilene. This central unit is called perilene. If you see the absorption maximum of this compound, absorption spectra, it starts say for around 420 nanometer up to, it goes up to 530 nanometer, and this is the region. The red spectra, whatever I am showing you, this is what is the absorption spectra. And this is the color of this compound. Okay, I will show you the color of other compounds also, then you will understand what I meant by the molar extinction coefficient. This molecule is highly fluorescent, and you see here, this is the fluorescent. What I did is, you take the same cuvette. This is a quartz cuvette in which I have now given the solution in chloroform. This molecule I have taken and dissolved in chloroform, and this is the color. If I keep this same cuvette inside a UV box where I have a UV lamp, this is what the color which I see. This is nothing but it's coming from the emission of these molecules, and you see the spectra of this molecule. This exactly gives that of the mirror image, kind of mirror image of this absorption spectra is shown here in the case of fluorescence. So this kind of property is very common in the case of polyaromatic hydrocarbons. Usually your absorption and emission are supposed to be mirror images to each other if they don't have much structural distortion in the excited state. So this is what I wanted to show you here. This molecule, as I mentioned, it has a strong absorption in visible region. And see, the visible region is starting from 400 nanometer to 800 nanometer. So that's why I wanted to show you the UV spectra. It has very good fluorescence quantum yield. Quantum yield is nothing but how many number of photons are hitting the molecule and how many number of photons are coming by the way of fluorescent photons. That is what we call as a quantum yield. So this quantum yield is near unity in the sense, whatever the photons which are absorbed by the molecule, the same amount of photons are coming out as an emission. That's what we are talking about here. And because of this, the electron deficient nature of this molecule, these molecules can be considered as an N-type semiconductor. And as I mentioned earlier, these molecules are used as organic field effect transistors and organic photovoltaic cells and so on. Now, when you go for light harvesting, why did I choose these molecules? So light harvesting is a very important concept when you are talking about, say, chlorophyll's case. The whole food, whatever we are consuming at this moment, everything is coming from photosynthesis. There is nothing called artificial food what we are having. So for this, completely you are depending on agriculture, and that is completely dependent on solar light. But if I want to have an alternative energy source, instead of using, say, for example, I don't want to use fossil fuels, and I want to use some other energy which is easily available and it is less polluting, then what you need is, you need to find some energy sources which is going to solve this purpose. For that, the easiest way is, if I can make some molecules just like that of chlorophyll, and that molecule absorbs the light, but it is not going to make paratha or food for us, but it is going to make some energy. It gives us some energy. Using that energy, I can do other purposes. So, for example, I can use it for electricity, or I can use it for chemical reactions and so on. This is what is called light harvesting. So when you go for light harvesting, what you need is, this is the solar spectrum which I have given you. This starts from around 300 nanometer, and then it goes up to 2600 nanometer. So if I find a molecule which absorbs in this region, okay, this is a solar light spectra, and if I have a molecule which absorbs in this radiation, then I will be able to harvest as many photons which is coming from the solar radiation, then I can convert them into chemical energy or electrical energy, and then I can use it for applications. This is one idea. Now, if you go for this simple porphyrin, which is a close relative of your chlorophyll, you see the absorption maximum of this compound. This is absorption maximum is around 410 nanometer, and then it has a small absorption which is around 550 nanometer. Okay, so the chlorophyll, what we are talking about, it is not absorbing the whole energy range, whatever it's here, but it is absorbing in some particular region. But there are some reports in which people have made solar cells using only porphyrins. In that case, what is happening is, the porphyrin is able to absorb light only in this region. As a result of this, the efficiency is not very high. So if I want to increase the efficiency, what I should do is that I have to functionalize this porphyrin, and I have to make sure that this molecule absorbs in other region also, so that the efficiency is going to be more. So what we thought, you see this region where it is absorbing is 400 nanometer, and then it is absorbing around 550. Okay. If I find a molecule which absorbs in this region where there is no absorption of porphyrin, then we can make sure that at least from 400 to 600 nanometer, this molecule can absorb light, and then we can increase the efficiency of this molecule. This was the idea. So that is why we chose porphyrins and Rilin diamides. So I can now choose different Rilin diamides to choose whichever the wavelength region I want to observe. Say for example, if I want to cover this region of solar emission, solar light, then I can use PBI. If I want to use this region, I can use QDI or longer Rilin diamides. So I have a tunability. I can choose whichever the molecule I want, I can fix it, and then I can make the molecule absorb in that region. So that is what is our idea. It's like a modular kitchen kind of thing. Whatever you need, accordingly you fix these accessories. So this is what I showed you earlier. So first we started with the functionalization of these molecules. I'll show you some synthesis point of view, then you will be able to enjoy what is so important in these cases. This is the starting material. This starting material is available much cheaper. See, this is the 2,000 rupees or so for 500 grams, and this molecule is the one which is used as a paint in cars. From here, we make this molecule. Because this molecule is completely planar, this is not soluble in any organic solvents, even in water it is not soluble. So you have to make this molecule soluble. So how will you make it soluble? Because this is insoluble because of pi stacking. So these molecules have stacked against each other, so these are not soluble. So if I want to make them soluble, I have to stop this pi stacking. So how will I stop this stacking? So what I do is, you take this molecule, you put a substitution here, this substitution is going to be sterically bulk. So when I make this group sterically bulk, then it doesn't allow another molecule to come and sit over this. As a result of this, this molecule becomes soluble. Okay. So now I made this molecule soluble. Now if I have to connect something here, I need to have some functional group so that I can connect this porphyrin or whatever the substitutions here that I can connect here. So we went for a simple bromination, and in this case we got some mixture of products. I don't want to get into a pure synthetic presentation. Just you remember that mostly we will be using only this molecule, which was quite good in amount, which is 57% yield. Comparatively, we are happy with this. Okay, ideally it should be more, but we are happy with this one to start with. After having this bromination, this is our starting material. So we got a crystal structure for this molecule. So why do you go for crystal structure? Now I say that I did this reaction, I got this product. So how will I prove this? So either I have to show some spectra, like Professor Muthuswamy was talking about this NMR spectra. I can give this NMR spectra for this molecule, but the same NMR spectra can be given in this case instead of bromine. If there is going to be another chlorine also, then in that case also I can give a spectra, NMR spectra. It will give more or less the same NMR splittings. So X-ray crystallography, what it does is, of course, mass spectrometry can help you in find out whether it is going to be chlorine or bromine. But more direct way of saying is, you can have a single crystal X-ray diffraction. So what you are doing is crystallize your compound, make it in a small crystal, then you keep it in an X-ray diffractometer, you irradiate with the X-ray, and then you find the diffraction patterns, and from the diffraction patterns, you get to solve the diffraction patterns using symmetry, and then you will be getting the structure of this molecule. What you are seeing here is the structure of the molecule in solid state. So if you see this, this is the monobromo perylene bicimide, and the bromine atom, you can see that it is protruding outside. Why this is protruding outside? Now you see this molecule. This molecule is the one here we are having this bromine. So this particular unit, this has a CH bond. This here it had a CH bond, and here also it has a CH bond. So this bromine, when it is going to be here, bromine is bulkier. So as a result of this, this bromine will be facing some steric repulsion from this carbon and hydrogen. And as a result of this, this bromine just goes out of the plane, and then it is sitting here. So now this is the plane of the molecule. I have shown it this way so that you will be able to see that the bromine is protruding outside. And after that, we went for functionalization. What we did is, we wanted to extend the pi conjugation. So extend in the sense, what you do is, you increase more double bonds or unsaturations. In this case, instead of double bonds, we increase the triple bond. This is a CC triple bond, and then which is connected to a phenyl. So what you are saying is, I have already here two naphthalene rings connected to each other, and other than that, I am increasing again the pi conjugation. So what I am aiming is to reduce the homolumina gap much more further, so that the molecule absorbs on the red side, and then it becomes much more absorbing. That's what the aim behind this. And the sideways structure of this molecule is what I have given here. You see this one, in this case, the molecule is completely planar. So why? In this case, bromine was there, the steric was there, so this bromine was going out of the plane. But when you have atom which is going to be sterically less bulky, then there is no much steric hindrance between these bay positions. So this molecule becomes planar. So this is one of this work which earlier we wanted to try that whether this, whatever the hypothesis we are talking about porphyrin and Rayleigh diamide, whether it will work or not. So let's first try with the phenyl rings. That is why we chose phenyl here. Then we went ahead. And thanks to Professor Tilagar, he was talking about charge transfer. So when you have one electron rich moiety and one electron deficient moiety in a single molecule itself, then the electron charge from the electron rich moiety can go towards the electron deficient moiety, and thereby it will be facilitating a charge transfer. So this kind of experiment we wanted to see that if I have an electron rich NN dimethyl amino group on the phenyl ring, which is there in the previous case which I showed you, whether we are seeing any charge transfer. So this is the spectra, the red spectra what I am showing you here is for this molecule. But a simple PBI, how it is looking like is the blue spectra. So you see this, the blue spectra, whatever I have here. In this case, it's a simple PBI, and only with phenyl without this NN dimethyl amino, that is what is given in green. In this case, the pi extension was there. As a result, the absorption is shifting towards the red side, but not much. But in the case of NN dimethyl amino, as soon as I put that, what is happening is electron density from here, it goes to the PBA, and as a result of this, there is a charge transfer, and the charge transfer gives way to another absorption. So that absorption is the one which we are seeing here. Now you see the molecule which was absorbing only from 400 to 600, the same molecule, having a proper appropriate functionalization as it was discussed in the previous talk, this molecule can be made to absorb in a wide range. Okay, so this is what the advantage of this class of molecules, that we can easily tune their pi surface and then we can make them to absorb or emit in whichever the region we want. So this was the idea behind this whole experiment. Whatever I have given in the bottom is HOMO and LUMO frontier molecular orbitals using density functional theory. So this are the nothing but electron density of this molecule at the ground state. Now if you see that the electron density is completely on this group, NN dimethyl amino, this is nothing but the same structure which I have given here, and above this I have shown the electron density. Okay, in the case of excited state, this is the LUMO, this is HOMO, and this is LUMO. The LUMO case, if you see that the complete electron density is going towards your PBA moiety, so that shows that this is the donor and this is the acceptor. So from here the electron density moves to this case, and as a result of this you are seeing this charge transfer transition what you are seeing here in this case. Okay, so this is one way. I am not getting much into this. There are a lot of compounds in the same direction we have made to see that whether the this molecule itself can be made to absorb in a wide range of wavelengths to check this. So these are some of the examples, and if you are interested, you can go through this papers, or if you wish, I will be sending you if anyone can contact me. Another idea is, instead of going for pi extension, can you use pi expansion? So what I am doing is, don't make the molecule taller and taller, but make the molecule stouter and stouter. Okay, so that is what is happening in this case. So we did some transformations, simple chemical transformation. Don't get into the mechanism behind this. At this moment, I just want to talk about the structure of this molecule. What we have done is, we have not increased the molecule in this direction, but we have made the molecule a little bit expanded towards the horizontal direction. So in this case, you have a 7-membered ring, and there also you have the phenyl ring. So you start from the simple PBI, how this is looking like. I will show you the comparative absorption spectra. This is the absorption spectra of the starting material. And when you have phenyl, you have this is the molecule. And when you have this substitution which is forming, now you see the molecule absorbs from 400 nanometer till 800 nanometer. The absorption is there. In this case also, the charge transfer is coming because of this nitrogen. This nitrogen is directly connected to this PBI, and this unit is electron deficient, and this nitrogen is electron rich because of the alkyl groups connected here. As a result, there is a charge transfer, and this molecule gives me an absorption in this stage. But in all the cases, the problem is the molar extinction coefficient of this molecule as such is very, very less. If you remember the first spectra which I showed you, the molar extinction coefficient of this molecule is around 50,000. So this is much less compared to that of porphyrin's absorption. Okay, and we tried another class of molecules also to make the molecule more and more electron rich, and this is what has been given here. And these are some of the annulation induced panchromatic absorption which we have given. Now we will go for, why did we go for PBA porphyrin assemblies? As I mentioned earlier, if I connect this PBI with the porphyrin, then I will be having a molecule which will be having absorption in this region as well as absorption in this region also. So I will be absorbing a wide range of solar radiation. And we were not the first to think in this direction. There are people who have thought about this one. So this is one report from one group called Vasilievsky's group from US. These people have made the molecule in which what they have done, you take this pyrrolene bicimide, take the porphyrin, connect them on this alpha position, so in the para position of this phenyl, and then you check this property of this molecule. Another group, they have taken, this is by Professor Marder's group, they have taken the porphyrin and the PBI and they have connected through an alkyne bridge. So why I have given selectively these two examples, there are few examples already in the literature. In this case, there was a spacer, and in this case, there is no spacer. In this, here the spacer is going to be only a triple bond. If you remember, in our case also, I took the PBI and connected with the phenylacetylene, and in that case, you had a triple bond and connected through a phenyl. The same thing is being done here in the case of porphyrin here, and in this case, they have done using a phenyl. When you use a phenyl group in between this ring and this ring, what is happening? You have PBI and you have porphyrin, and in between you need to have a seamless orbital overlap. If these two orbitals of porphyrin and PBI are not overlapping, then these two molecules will not talk to each other. As a result, you will not have any charge transfer. If you don't have charge transfer, you will not have any absorption in the red-sided region. So this is one of the problem because there is no pi extension in this case. The second case, you have porphyrin and you have PBI, and then again I have porphyrin, but these two guys are connected through a triple bond. So when you connect through a triple bond, what is happening is these two molecules come more or less planar. When you become more or less planar, there will be an effective orbital overlap between the PBA and the porphyrin. So that makes this charge transfer much more feasible, and the molecule absorbs in the red region. Yes, the second example actually absorbs in the red region, but there is a problem. If you remember the pi stacking, what I was talking to you earlier, when you make a molecule longer and longer, I told you that this molecule becomes lesser and lesser soluble in the solution because of the pi stacking. So in this case, this is also the same thing is happening. I have porphyrin that also has a pi surface. I have PBI. Again, I have another porphyrin. So as a result, this molecule, when you become larger and larger pi surface, this molecule becomes more and more prone to aggregation. As a result, the solubility goes down. Once the solubility goes down, it becomes very difficult to synthesize this molecule. Even after synthesis, you cannot purify this molecule because it's not soluble in anything. So you cannot do column chromatography or whatever the way, you cannot make this molecule pure. But when you want to go for solar photovoltaic applications and light harvesting applications, the molecule should be extremely pure so that we know that where from this harvesting is happening. Okay. So take this as a challenge. We wanted to go for making a molecule which is soluble, but at the same time, it has all the photophysical properties of this molecule. The advantages should be there, but the disadvantages should be removed. That is what we started with. This may look like a total synthesis for a starter, but in this case, this is a simple porphyrin synthesis. Usually, it is being done in porphyrin literature, and you have to go through all the steps, and then we are making this porphyrin. After that, we go for a Sonogashira coupling reaction, and then we are getting this porphyrin PBI link. In this case, intentionally, we have chosen only one PBI and one porphyrin. I did not go for two porphyrins. I don't want to reinvent the problem, whatever they have. So in this case, we just wanted to see whether can we solve this problem. But to our surprise, the molecule, whatever we synthesize, this is soluble even in a simple chloroform, which is easily available in any synthetic lab. And the NMR, whatever I have given you, this is recorded in the CDCl3, deuterated chloroform, which is being used for recording the NMR. Second feature is, I have marked here two units. One is the orange peaks, orange markers, wherever I have given. This is coming from the PBA backbone, the protons which are there in the PBI. And the purple ones are given for the porphyrins, which is coming from here, and all these peaks are given. If you see the NMR spectra of this, the signals of this NMR spectra, which are very sharp. So what it means is this molecule do not have any aggregation in solution when I am recording EPA, when I am recording NMR. That shows that this molecule somehow avoids aggregation, and then it was very difficult to see that why this is so. When we found the crystal structure, single crystal structure of this molecule, this was one of the first structure when we did for the PBA derivative. Earlier PBA was supposed to be so-called, it's difficult to crystallize, but this is one of these large molecules where we could crystallize. And in this case, if you see the porphyrin and PBA both are in the more or less the same plane. But what we did is when we were kept for the crystallization, we added a little bit of pyridine so that this molecule will go and bind to the zinc which is there at the center, and in this case it's nickel. it will go and bind to the nickel. And as a result, what happens is another porphyrin cannot come and sit over this porphyrin because this porphyrin already has a pyridine ring which is bound to this. So this is what is making this molecule soluble, and as a result, we could get a crystal structure. And the crystal structure proved that when you connect these two using a CC triple bond, the molecule is actually planar. If this molecule is now planar, then what I need to see is that whether this molecule has all the photophysical properties what I expected, whether there is a charge transfer. And if charge transfer is there, then I should see an extended absorption. Now I show you the three molecules. This is a normalized absorption. Normalized absorptions in the sense, even though the molar extinction coefficients are different, I am showing it for illustration that these are all more or less the same. Now you see this PBI. This is the spectra which you would be seeing for the PBI. And this is for porphyrin. This is the absorption spectra of simple porphyrin. And when I connect these two using the CC triple bond, what I'm saying is, you see the absorption spectra of porphyrin, absorption spectra of PBI, which is diminished. I'll tell you why it is so. And third one, I'm seeing that the charge transfer transition which is coming here. So the charge transfer transition, what it does is, it has made this molecule absorbing up to 850 nanometer. So if we remember earlier, if I am talking about only porphyrin and PBI, ideally this molecule should absorb only up to this point. It should not have any absorption in this point. So this absorption is coming because of the charge transfer transition, which is happening because between PBA and porphyrin because of the CC triple bond. What the CC triple bond is doing is, the CC triple bond makes sure that this chromophore, that is PBI, and the porphyrin chromophore both couple with each other. As a result of this, there is an effective orbital overlap, and then that makes this charge transfer much more feasible. Now the question comes, how do you know that it is because of that one or it is because of something else? Okay, now you take simple solution of PBI, only PBI, and then another solution in which is you are having only zinc porphyrin, mix both of them. And in that case also, what you have is, in solution, you have PBI as well as you have porphyrin. If this molecule is, if the mixture is absorbing light around in this region, then it is not because of only the triple bond, it is because of something else. But in this case, if I mix these two, the spectra, if you see here, what I'm saying is simple absorption spectra of porphyrin, simple absorption spectra of your PBI, and there is nothing here. But the molecule which we made, that molecule is having here. This is showing that the covalent connectivity between these two units actually plays a vital role in making this molecule absorbing in a wider range. That is what I wanted to show here. And we can change the the nature of metal which is there inside the porphyrin. So we have tried with the different metals, nickel, copper, and zinc. In our experiments, we could see that the zinc was the one which had longer absorption window and then makes this molecule much more useful. And this is the absorption spectra measured in thin films for just solar photovoltaic applications. We do electrochemical studies as well as computational studies for these molecules to make sure that this molecule's redox properties, whether it has changed. If the redox property is changing, then we can get more information from this. So that is why we are doing cyclic voltammetry. The cyclic voltammetry shows that whether this molecule is easier to oxidize or difficult to oxidize and so on. Because of the presence of electron deficient PBA connected to the porphyrin, so it pulls the electron away from the porphyrin. So as a result, if I want to oxidize this porphyrin, that means if I want to pull one electron, it becomes difficult. So oxidation of these molecules, whatever I have made, it becomes difficult, but reduction of the molecule becomes much more easier because it's already electron deficient unit. So this becomes easier to reduce, but rather than porphyrin's case, it becomes difficult to oxidize. These are the observations which we had, and this is the HOMO and LUMO. You can see the HOMO is completely on the porphyrin. That means that the electron density is on the porphyrin in the ground state. When you go for LUMO, then the electron density is completely on the PBI. It shows that there is a charge transfer in this case. Then, all this story I made telling you that whatever the molecule we are going to make, it is going to have fantastic photovoltaic properties. Light harvesting is going to be very good. And then after that, I am going to make a big solar cell. But actually, it doesn't work that way. And you see these values, whatever we are having here, this is the photocurrent conversion efficiency, 6.18%. That means out of the light, whatever we are shining, we could harvest only the 6% of this. Of course, there are other parameters which define this one. At least you remember that the 6 value is not very high. It is okay. For the first time you are trying something and you are getting. This is the structure of the solar cell which you have used. And if you see the incident photon conversion efficiency, in this case, from 350 nanometer till 800 nanometer, this molecule actually absorbs. When I am using this molecule as a donor, and you have to use another molecule as an acceptor, in this case, we have used PCBM, which is a fullerene derivative, C60 derivative. And that derivative we have used for absorption, as an acceptor. And then this is the efficiency we could get. So now the question comes whether this will work only for this system, whatever we have made, only one porphyrin and one PBI. Can we make it larger? So always the greed is the source of the problem. So in this case, again, we went for much longer systems. So this is the molecule which we made earlier. So we could make this molecule dimerize. And as a result, now what I have is, I have 2 porphyrins and then 2 PBIs connected to each other. So then that means that the molecule should absorb much more widely. Okay, that's what expected. This molecule is also for us luckily soluble, and then it gave fantastic NMR. So this molecule is not having much pi stacking, so it's good. This is the absorption maxima. Now you see the absorption maxima, you will feel the difference what I am talking about. PBI, I have placed it especially with respect to molar extinction coefficient, so that you can maintain the, you can appreciate the values. This is the absorption maxima for PDI. Berlin diimide, and which is having around say 50,000 to 75,000 depending on the substitutions. And when you see this molecule, when I have zinc, okay, this is the orange one. You see the spectra which starts from say for example 370, it goes up to 900, but see the molar extinction coefficient, it is 3 lakh. It's much more intense in absorbing than that of your PBA, simple PBA or simple porphyrin. And why I am saying is then simple porphyrin is much more stronger. But if you see the range in which it is absorbing is very, very narrow. But in this case of compounds, you are absorbing in a wide range of wavelengths, but at the same time with a very good intensity. So that makes these molecules much more efficient. So this is the same experiment we have done here also. Just mix PBA and porphyrin and then see that there is no charge transfer here that we know earlier. But in this case, you are seeing this band that is becoming because of this direct connection, which actually enhances the charge transfer. And this absorption spectra here, this is called a Sorad band. So cytochrome P450, we say that the 450 is nothing but the absorption maxima. And the absorption maxima is coming because of a band called Sorad band. Okay, so this Sorad is coming from a scientist name. This Sorad band is the one which we are seeing here in the case of simple porphyrin is around usually around 400 to 410 nanometer. But in this case, this is split. So this splitting is because of 2 chromophores which are connected directly to each other. So then another concept comes into picture called excitonic coupling. If you are more interested, you can contact me. I can give you some materials to read about it. But that is why this spectra is splitting. It is not because of 2 porphyrins are there. That's why 2 peaks are coming. It is not for that. Of course, we have done electrochemical investigations of these molecules as well. And we could find out the energy levels of these molecules and then found that these molecules, we are yet to do solar photovoltaic studies. Some preliminary studies we did, but it was not that successful. Now the question comes, you are talking about a porphyrin and a PBA which are connected through a triple bond. If I connect directly, will I have more more charge transfer because these 2 molecules are going to be close to each other? Okay, let me see that we took this as a challenge and then we made these molecules as well. This is the synthetic scheme of this one. We could make a trimer and a tetramer for these molecules, and all these molecules have been structurally characterized. This is not a small task, but it's unpublished data, but I'm just showing you that this is not easy to crystallize these molecules. And these molecules are not having any solubility issues. Why there is no solubility issue? If you see that these 2 molecules are directly connected, these chromophores. Once you connect one phenyl ring with another phenyl ring, both the phenyl ring and biphenyl are not going to be in the same plane. They will be always perpendicular to each other, or there will be some angle. Okay, the same thing is happening in this case. You have PBA and then you have a porphyrin. When you connect these 2 systems directly to each other, then they are not going to be in the same plane. So in this figure, you can see that this is in one plane and this is in another plane. So as a result of this, these molecules will not have much pi stacking. Because if I want to stack one porphyrin, will want to stack another porphyrin, this PBI will not leave it to stack. So as a result, these molecules become much more soluble. But the loss is here. Molecule solubility was very easy, very nice, and the molecule behaved very well. But the problem is, now if you see this absorption spectra of this molecule, say for example, it gives me the same broad absorption as expected in the case of previous directly connected porphyrin. But if you see this area, the absorption, whatever I was seeing as a charge transfer, which is the more intense peak, that's missing. That is nothing but that is because of the direct connection between these two, and these two rings are not in the same plane. If they are not in the same plane, then there will not be any orbital overlap between porphyrin and the PBI. And if there is no effective orbital overlap, there will be no charge transfer. If there is no charge transfer, then you will not have any absorption here. That's what the final conclusion between this. Okay, now we went from one porphyrin to two porphyrins. Now the next question comes in like, can we go it for another set of molecules? So here I am just showing you some of the molecular orbital diagrams. This is the HOMO and this is going to be the LUMO. You can see that the electron density is always on the porphyrin because that is electron rich in the ground state. When you go for the higher next up LUMO, then you will be seeing that LUMO is completely localized on PBI. So now the question comes, why it should work only with PBI? Why don't we go for NDA? So now we realize that the triple bond is mandatory. If this triple bond is not there, then you are not going to get the charge transfer band. This is straight and clear. Now, why don't we go for a smaller molecule? If I go for a smaller molecule, there is a loss because this molecule is smaller. So my absorption will be shifted towards the blue side. And at the same time, the absorption coefficient also goes down. But still, this molecule is very difficult to make. So we took it as a challenge and then we tried to make this molecule. We went for the same reaction. We could get this molecule in decent yield. And we have done all the studies, whatever was expected. In this case also, you can see that there is a charge transfer. So this charge transfer is coming because of the triple bond connection between NDA and the porphyrin. As a result, this molecule also absorbs in very extended region from 400 to 850 nanometer. And now when you see the absorption spectra in thin films is you take a quartz plate and above this you coat this molecule and then record the spectra. You can see that this molecule actually absorbs very strong from, say, for example, 400 nanometer to 900 nanometer. That's because the molecules stack over each other, and as a result, the absorption actually goes up because of the intermolecular charge transfer also, which comes into picture in these cases. So that is the one. And in the case of NDAP also, we have tried electrochemical studies. In this case also, we could see that these molecules are structurally and redox-wise, they are robust. So there is no problem with respect to these molecules. And this is the frontier molecular orbitals. Again, the HOMO is on the NDA. HOMO is on the porphyrin, and this is HOMO. This is electron density is on the porphyrin, and this is LUMO, where electron density is on the NDA, which shows that the same thing, whatever we decided in the case of PBI, it works for NDA also. We made a solar cell for using this molecule as a donor again, and then we use this PCBM as a acceptor in this case, and then you see the value here. So last case when I was showing you, it was 6.1, and in this case I am talking about 8.45. And in that case, what we had is a longer PBI, but in this case we had a shorter NDI. So what it says is, it doesn't matter whether you are going for longer or shorter, but if the orbital energy levels of this porphyrin and PBI or any Riley diamide, if they are going to be suitable, then you will be having much better absorbance or much better solar photovoltaic application for this. Now the question is, now you went for PBI, shorter version of PBI, which is NDI. Can you go for longer version of PBI, which is TDI? So we took this also another work, and then we can go for it. And then in this case, as I mentioned earlier, you'll be having much better absorption coefficient for this class of molecules. So this will equal to that of porphyrin. And in this case, you'll be seeing this. So this is the typical synthesis of these molecules. And then we made some molecules in line with the PBI to check whether this molecule also behaves the same. And we were lucky to get some crystal structures for these molecules as well. And this is the tetra-bromo derivative, and this is the tetra-acetylenyl phenyl derivative. And this is the structure. In this case, you see that this molecule is not planar. So what is happening is, it's like 4 hands of these molecules, and 2 are in one direction and 2 are in another direction. What is happening is, this naphthalene ring and this naphthalene ring, actually they bend. They twist with respect to the central naphthalene ring. As a result, these 2 phenyl rings are, one is going up, one is going down, and these 2 phenyl rings are one is going up and down. So, and central naphthalene ring exactly planar. So this is because of, when you go longer and longer, the flexibility becomes more and more good, and after substitution, of course. And this is one of this, side effect of this crystallization. We could see some direct bromine-bromine bond here. When you say bromine-bromine interaction, we have to first take into consideration of this van der Waals radius of these two atoms, bromine, and then you have to see that is around 3.7 angstrom. But in this case, we are seeing 3.3 angstrom. That means that it's coming closer than the van der Waals radius. That means there is some interaction between these two bromines. So currently, we are working on some charge transfer, charge density studies on these molecules. Most probably, in the next time, if I visit the college, then I will be giving you an extended presentation on this one. So let's go for the optical properties. This is what I was claiming high. Now you can see that where I had this NN dimethylamino case, yes, in this case also we have a charge transfer, and the charge transfer makes this molecule absorbing up to 900 nanometer. And you see this absorption maxima is also quite good, or the molar extinction coefficient. So that shows that this molecule, if I connect porphyrin to this one, this molecule can behave very well. And another advantage of this molecule is, if you see the fluorescence of this molecule, it actually goes towards the red side. So that means these molecules are, emitting in near infrared region. It's very good for bioimaging studies. Studies in this direction are going in our institute. So this is the same cyclic voltammetric studies as well as the density functional studies. And this is the optical and electrochemical data, whatever we have summarized here. And these molecules are also highly fluorescent as well as they absorb very strongly. Now, when you go for this one, this is fine. Can I connect this TDA porphyrin? And now you see this. This is the absorption spectra of porphyrin and absorption spectra of TDA, which are connected to each other, which are independent. I'm just mixing the solution, and then I'm showing you this is the spectra, not mixing the solution. I'm giving two independent spectra and then plotting it together. So if I make a porphyrin TDA together, then I should be having absorption ranging wide, because this is 400 nanometer and then it's going up to 700. Then the charge transfer will make it absorbing in NAR. So towards the direction we went for this molecule. These are the NMR spectra. Fortunately, you see all the spectra are sharp. All the peaks are sharp. That shows that this molecule, in our hand, fortunately, we didn't have any aggregation-induced problems, and the solubility is very good. Crystal structure is known. Crystal structure we have reported. And these molecules have been made. Now, we have made both the molecules in this case. One is directly connected, another is connected with acetylene to see that whether there is any effect. Now, you see this is the absorption of TDI, and this is the absorption of porphyrin. When I connect this TP1 is directly linked one. Okay. So, in the case of TP1, the brown spectra, the charge transfer is not much. That means ultimately there is no charge transfer in this region. But you see the TP2 in which we have connected this molecule using the acetylene bridge. So as a result of this, now you see that this molecule has an absorption. This is coming from the TDI, and this is coming because of the charge transfer. So that means this molecule absorbs from 400 to 900 nanometer very nicely. So this is where now if we can go for a dimerization of this molecule again, then what I'll be having is, we will be having a fantastic molecule which will be absorbing even in the near infrared region, which is above 900 nanometer. This is one of the aim currently we are working on this one. Most probably we will be getting. But in the earlier examples, whatever I talked, if you remember the absorption of PBI or NDI with respect to the porphyrin in the connected ones, this band, whatever you will be seeing, this will be always in lower intensity, and the porphyrin peak will be always in higher intensity. That is because this porphyrin has higher molar extinction coefficient, and NDI and PDI have less, molar extinction coefficient is very less. As a result of this, even though one molecule of porphyrin and one molecule of NDA are there, but their molar extinction coefficients are different, so you will not see that the spectra both are going to absorb at the same intensity. So that is what it is seeing. But in this case, if you see that even after connecting to the porphyrin, you will be seeing that what is the absorption coming from TDI, you can clearly see, because this absorption maxima is more or less comparable to that of your porphyrin. So this is what I wanted to show, that if I go for longer derivatives of these molecules, now from TDI I go for QDI, that is quartal diamide. So I have 4 naphthalene units. In that case, I'll be having absorption around this region, and at the same time, molar extinction coefficient will be somewhere here. So that means this molecule, whatever we would be making, that will start from 400 nanometer, it will be absorbing up to 1000 nanometer or 1100 nanometer. That's much useful for solar photovoltaic devices. This is what is our conclusion at this point. And this is the usual experiment which we used to do, the mixture of TDA and porphyrin, and this is what is given for your reference. And electrochemical data shows that these molecules are very robust and they are stable, they don't decompose. And this is the density functional theory data which has been given. And all this work, of course, this is not done by me, even though I claim that I have done, but all the things are done by the students. And you can see that my group, people are not sad, but everyone is happy. And these are the guys who make these molecules, and I am the person who comes and presents and then takes all the credit. And this work was, PBI was started by Ruchika, and after that it was taken forward by Ram Prasad. He is currently in IIT Gandhinagar, so he is not around in this picture. And now it's been taken care by Ayushi. I don't know, she is also not here in this picture. Now Kundan is working on this, and Shivangi is working on. So these are the 4 people which they are working on in this particular direction. And we have, of course, without collaborators, we will not be able to do the physics studies, whatever we have done here. Professor G.D. Sharma from LNM IIT Jaipur, he is helping us with photovoltaic studies. Professor Bautermeier is also helping us in photovoltaics. Professor Dongo Kim helps us in recording photophysical studies of some of the molecules and related to charge transfer. Professor Ajay Minu from University of Newcastle, Australia, he is part of a SPARK project, so we are working on a two-dimensional materials related to porphyrins. Professor Vimlesh Kumar, he is helping us in bioimaging. I have not talked about this here, it's a totally different area, so I did not bring it here. And we have a center in our institute, which is called Center for Research on Environment and Sustainable Technologies for making sensors for different anions and cations and so on for groundwater detection. So that work is a different work, so I have not brought in this particular presentation. With this, the conclusion is that the work, whatever we have discussed here, all these molecules have been made in India, but even though earlier people were thinking that this molecule cannot be made because these are very difficult to characterize. But at this point, the kind of facilities, whatever we have in our institute, we will be able to characterize or do any kind of research. And we are actively looking for students for PhD. And if any one of you, the students, undergraduate or PG students who have GATE or CSIR or UGC, JRF, you are free to contact us. Our department, we are always looking for PhD students from various corners of the country. And I always encourage you to apply to our department. We will be soon sending our advertisement. If you are having any doubts, you can always contact me, and we will be happy to share any information we have from our department. And now I thank the Vivekananda College department for giving me this opportunity, and thanks for the patience, and thanks to Professor Mail Murugan and team for giving us this opportunity. Jai Shri Guru Maharaj Ki.
Thank you, sir. Thank you for your thought-provoking and informative talk. And I request all the, if you have any doubts, you can post it on the comment box. I think I have one question from Dr. M. Ganapathy, sir.
Yes.
Can I ask you, sir? Yeah, okay.
Yeah,
so, what is your opinion about commercial use of dye-sensitized solar cells compared to silicon solar cells?
You're putting me into trouble, I think. Hopefully, no one is working on DSSC at this point. Okay, so silicon solar cells, they have their own advantages, and DSSC has its own advantages. Okay, so at this moment, it is premature to comment on this. Both the sides, the research is going on. Earlier, only crystalline silicon was needed, but nowadays, amorphous silicon also people are using. That brings down the price. But in DSSC, of course, there are a lot of improvements, and the efficiency also goes up. So at this moment, it is not a right way to compare it, in my opinion.
Okay. Okay, sir. Okay, sir. And another question from Dr. M. Ganapathy, sir. So, what about the stability and lifetime of dye-sensitized solar cells? How will you increase the lifetime of dye-sensitized channel?
Okay, so I would apologize for this particular thing, because I am not working on dye-sensitized solar cells. We are working on bulk heterojunction solar cells. So my knowledge in DSSC is, I would say, 0.
Okay, sir. So thank you for your highly informative talk, sir. And I thank on behalf of Vivekananda College and PG and Research Department of Chemistry. Thank you, sir. Thank you for your nice talk, nice lecture. Thank you, Anand.
Thank you, Raj, and it's really a good lecture. Fluorescence, colorful chemistry, no doubt you played a lot with porphyrins as well as naphthalenamide. So without further delay, may I request Dr. G. Balakrishnan, sir, Department of Chemistry, Vivekananda College, to register his formal vote of thanks. Welcome you, sir.
So, a very good evening to all.
It's given me immense pleasure to deliver the vote of thanks for the CRSI event to dignitaries assembled here. I would like to thank our chief guest, Professor S. Muthuswamy sir, Bharatidasan University, Trichy, Professor P. Tilagar, Professor J. Sankar, Isaac Pobal, who's honored this function with his inspiring thought like NMR spectroscopic, boron chemistry, and porphyrin ring like that is application to artificial light harvesting applications. It's a really eye-open talk. We are very happy to enjoy your lecture, sir. Because of organizing committee, we sincerely thank Professor Palniyandan sir to participate the entire session of the webinar, sir. I heartfelt thank Palniyandan sir. I would like to thank convener of Madurai Trichy local chapter, Dr. R. Mail Murugan, Madurai Kamaraj University, Madurai, Professor R. Ramesh sir, Bharatidasan University, Trichy, and coordinator B. Servar Muthu, head of the Department of Chemistry, Vivekananda College. I would like to thank our brother, Secretary Swamiji Maharaj, Vedananda, and Kulapati Swamiji Maharaj, Adhyatmananda, Principal Dr. T. Venkatesan sir, staff member of our college, and students and participants for making this function and webinar as a grand success. Finally, a heartfelt thank CRSI making offer to transfer of knowledge from legend of chemistry to new. Once again, I thank one and all persons here. Thank you to all of you. Thank you so much.
Thank you, Bala sir. So better indeed is knowledge than mechanical practice. Better than knowledge is meditation. Bhagavad Gita. So let me pray the Almighty journey together to rescue as early as possible from this dreadful pandemic situation of COVID-19. Be safe and stay is better than any vaccine. So with your hearty wishes, let me allow to disperse this one-day e-lecture workshop program and advances in chemical science organized by CRSI Trichy-Madurai local chapter, adjoining with the PG and Research Department of Chemistry, Vivekananda College, Vedagam West. Finally, national anthem by all.
भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड बलवंता विंध्य तव शुभ नाम तव शुभ जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय जय जय।
Thank you all. Meet you again with a new platform. Jai Sri Guru Maharaj Ki.
Thank you. Thank you, Professor.
Thanks, Manmohan.
Thank you, Tilagarana. Thank you, Muthu. Thank you, Ilayaraja.
Thank you, sir.
Thank you, sir. Thank you, sir.
Sorry, here. Make use of this offer. Send many students to Bhopal.
Yeah, I'm looking forward.
Okay. Thank you.
Thank
Thank you. So, thoroughly I thank Vivekananda College for hosting nice event. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you.
Sir, BSM sir.